When scientists first started studying the giant planets in our solar system, they thought that maybe one day we could live there. Jupiter and Saturn are huge, much bigger than Earth, and they seemed full of possibilities. But it turns out these giant balls of gas hold a terrible secret. There is no ground to stand on. If you tried to land on Jupiter, you would sink forever through layers of gas that get hotter and more crushing as you go down. The pressure inside is so strong that it would crush any spacecraft or person in seconds. This made scientists ask a sad question. Are there places in the universe that we can never call home? Get ready to fall asleep while listening to this video. Subscribe to the channel, leave your like and comment what part of the world you're watching from. Get comfortable and relax. Let's begin. Imagine trying to build a house on a cloud. That's essentially what colonizing a gas giant would be like, because these planets don't have a surface to stand on. When we think about colonization, whether it's on Mars or the Moon, we always picture a solid ground beneath our feet, a place to plant our flags and build our homes. But gas giants like Jupiter and Saturn are entirely different beasts. They're called gas giants for a reason. They're massive planets composed mostly of hydrogen and helium, with no solid surface in the traditional sense. This isn't just a minor inconvenience, it's a fundamental barrier that makes the very idea of colonization a fantasy. Let's break down why. First, understand what a surface means. On Earth, we have a clear boundary between the atmosphere and the ground. We can walk on it, dig into it, and build upon it. On gas giants, there's no such thing. The atmosphere just gets thicker and denser as you go down, gradually transitioning from gas to liquid-like states without a distinct surface. Scientists sometimes refer to a surface on gas giants as the point where the atmospheric pressure equals 1 bar, which is similar to Earth's sea level pressure. But that's an arbitrary definition, because at that point, you're still in the atmosphere. There's no solid ground. It's like saying the surface of the ocean is where the air meets the water, but for gas giants there's no ocean floor to reach. As you descend into a gas giant, the pressure increases dramatically. What starts as a thin atmosphere at the top becomes a dense, soupy mixture. Deeper still, the hydrogen becomes so compressed that it turns into a supercritical fluid, a state where it's neither truly gas nor liquid, but has properties of both. This happens at depths where the pressure is thousands of times greater than on Earth. In fact, the pressure increases so much that eventually hydrogen becomes metallic liquid, but that's far below any conceivable habitat. The key point is that there's no sudden stop, no crust to land on. Any colony or probe would simply keep sinking until it's crushed by the immense pressure. This absence of a solid surface poses a huge problem for colonization. Colonization implies establishing a permanent settlement, a place where people can live and work. But how do you settle on something that has no floor? You can't build structures that rest on the ground because there is no ground. Everything would need to float like a submarine in an ocean of gas. But even submarines need to adjust their buoyancy to stay at a certain depth, and they can rise to the surface. On a gas giant, there is no surface to rise to. You're always submerged in the atmosphere. Floating habitats might seem like a solution. You could design balloons or dirigibles filled with a lighter gas like helium to hover at a specific altitude where the density allows buoyancy. But that brings its own set of challenges. For one, the altitude where buoyancy is possible is often where the winds are incredibly strong. Jupiter's winds, for example, can reach speeds of hundreds of miles per hour, with jets and storms that last for centuries. A floating habitat would be at the mercy of these winds, tossed around like a leaf in a hurricane. Without any anchor, it would drift uncontrollably, making it impossible to maintain a stable location. Moreover, the density and pressure at those depths are already extreme. To float, a habitat would need to be at a level where the atmospheric density matches its own average density. But that level might be deep enough where the pressure is crushing and the temperature is scorching hot. Gas giants have internal heat sources, so temperatures rise with depth. On Jupiter, at the 1 bar pressure level, the temperature is around minus 100 degrees Celsius. But deeper down, it can reach thousands of degrees. A habitat would need to withstand both the pressure and the heat, which requires materials and technology far beyond our current capabilities. Consider the probes we've sent to gas giants. The Galileo probe entered Jupiter's atmosphere in 1995. It survived for about an hour, transmitting data as it descended, but it was eventually destroyed by the increasing pressure and temperature. It was designed to last only a short time, not to sustain human life. Even then, it didn't land. It just sank deeper until it was crushed. That's the fate of any object on a gas giant, perpetual sinking unless it has enough buoyancy to stop it at a certain layer. But buoyancy alone isn't enough for colonization. A colony needs stability, resources, and a way to expand. On a gas giant, there's nothing to build upon. You can't lay foundations or construct buildings that are anchored to the ground. Every structure would have to be self-contained and floating, which means it would be vulnerable to atmospheric disturbances. Turbulence, storms, and shear forces would constantly stress the habitat, leading to wear and tear that could be catastrophic. A single breach could cause the habitat to sink or lose buoyancy, dooming everyone inside. Furthermore, the lack of a surface means there's no access to raw materials. On terrestrial planets, colonies can mine the ground for minerals and resources. On gas giants, the atmosphere is mostly hydrogen and helium, with traces of other elements. To get anything useful, like water or metals, you'd have to process enormous volumes of gas, which is highly inefficient. Any construction materials would have to be imported from elsewhere, at great cost. This makes a self-sustaining colony practically impossible. The psychological impact is also worth considering. Humans need a sense of place, a horizon to look at, and a solid ground underfoot. Living in a floating habitat surrounded by perpetual clouds and storms, with no day-night cycle as we know it, could be mentally taxing. Knowing that below you is an endless abyss with no bottom could induce anxiety and disorientation. Colonization isn't just about survival, it's about creating a home, and a gas giant doesn't offer the conditions for that. In science fiction, we often see cities floating in the clouds of gas giants, but reality is far harsher. The physics of these planets simply doesn't allow for a stable surface. The very concept of landing is meaningless, because there's nothing to land on. Instead, you'd be conducting a controlled descent that never ends, unless you actively maintain your position with buoyancy or thrust. But that requires constant energy input, which is unsustainable for a long-term colony. So why is this important? As we look to the stars and consider colonizing other worlds, we need to understand the environments we're dealing with. Gas giants are fascinating objects for study, but they are not places for human settlement. They're reminders that not all planets are created equal, and some are forever beyond our reach as homes. Our efforts should focus on more hospitable worlds, like Mars or the moons of gas giants, which have solid surfaces and potential resources. To delve deeper, let's talk about the structure of gas giants. Jupiter, for instance, is composed primarily of hydrogen and helium. As you go from the outer atmosphere inward, the gas gradually becomes denser. There is no sharp boundary between atmosphere and interior. At about 1,000 kilometers down, the pressure is so high that hydrogen transitions to a liquid state. But it's not a liquid like water. It's a supercritical fluid that behaves strangely. Deeper still, at around 20,000 kilometers, the pressure reaches millions of bars, and hydrogen becomes metallic liquid, which conducts electricity. This metallic hydrogen layer is thought to generate Jupiter's powerful magnetic field. But throughout this journey, there's no solid surface, no place to stand. Now imagine trying to build a colony in such an environment. Where would you put it? If you try to float it in the upper atmosphere, the density is too low for buoyancy, so you'd sink. To achieve buoyancy, you need to go deeper where the atmosphere is denser, but that's where the pressure and temperature become lethal. The sweet spot for buoyancy might be at a depth where the pressure is already tens or hundreds of bars. For comparison, on Earth, the pressure at sea level is 1 bar. Scuba divers experience increased pressure underwater. But at 10 bars, which is equivalent to about 90 meters underwater, the pressure is 10 times greater. On a gas giant, to find density high enough for buoyancy, you might need pressures of hundreds of bars, which is unimaginable for human habitation. Additionally, the winds on gas giants are not like Earth's winds. They are sustained by the planet's rapid rotation and internal heat. Jupiter rotates once every 10 hours, which drives powerful jet streams that can reach speeds of over 300 miles per hour. These winds create bands and zones that circle the planet, with shear forces between them that could tear apart any large structure. A floating habitat would need to withstand these forces continuously, which would require immense structural integrity and constant adjustments to maintain position. Energy is another concern. On Earth, we can use solar power, but on gas giants, sunlight is much weaker. Jupiter is 5 times farther from the Sun than Earth, so it receives only 1/25 of the sunlight per unit area. At the depths where buoyancy might be possible, it's dark, so solar power is out of the question. You'd need nuclear power or other internal energy sources, but that adds weight and complexity. Plus, you need energy for life support, heating or cooling, and maintaining buoyancy. It's a vicious cycle. Let's consider the materials needed for a habitat. To withstand high pressure, you need strong materials like titanium or advanced composites. But even the strongest materials have limits. At pressures of thousands of bars, metals deform and fail. The habitat would have to be a perfect sphere to distribute pressure evenly, but spheres are not ideal for living spaces. Any windows or openings would be weak points, and if you're importing all materials from Earth or elsewhere, the cost would be astronomical. Now think about daily life in such a colony. You're stuck inside a sealed environment, with no way to go outside without a spacesuit that can withstand extreme pressure and temperature. But even spacesuits would be impractical because the atmospheric composition is toxic. Jupiter's atmosphere contains ammonia, methane, and hydrogen sulfide, which are poisonous to humans. A leak could be fatal, and if you try to go outside, the winds would sweep you away instantly. What about expansion? On a solid planet, you can build new structures adjacent to existing ones. On a gas giant, every new habitat would have to be a separate floating unit connected by bridges or tunnels, but those connections would be vulnerable to winds and turbulence. It's like trying to build a city on floating platforms in a stormy sea, but worse because the sea is made of gas that gets denser with depth. Some might suggest using aerodynamic shapes to navigate the winds, like airships. But airships on Earth rely on relatively calm conditions. On gas giants, the winds are chaotic and unpredictable. There are storms like the Great Red Spot on Jupiter, which is a giant anticyclone larger than Earth, with winds swirling at over 400 miles per hour. A habitat caught in such a storm would be destroyed. Moreover, the lack of a surface affects everything from transportation to waste management. On a solid planet, you can have roads and vehicles. On a gas giant, all transportation would have to be through the air, using thrusters or balloons, which consumes energy. Waste disposal would be tricky. You can't bury it, so you'd have to recycle everything perfectly, which is challenging in a closed system. From a scientific perspective, gas giants are invaluable for understanding planetary formation and physics, but for colonization, they're a dead end. The absence of a solid surface is not just a missing feature, it's a showstopper. It means that all the techniques we've developed for living on planets, agriculture, construction, mining, are useless here. We'd have to invent entirely new technologies from scratch, and even then, the environment is so hostile that it's hard to justify the effort. In the grand scheme of space exploration, we should focus on where we can actually live. Moons like Europa or Titan have solid surfaces, albeit with their own challenges, but they offer more promise. Gas giants will remain destinations for robotic explorers, not human settlers. So while the idea of floating cities on Jupiter sounds cool in movies, in reality it's an illusion born from our desire to conquer every environment. Some places are meant to be studied, not inhabited. To sum up, the illusion of a surface on gas giants is a fundamental barrier to colonization. Without a solid ground, we lack the foundation for building a settlement. Floating habitats face immense challenges from pressure, temperature, winds, and the lack of resources. While it's fun to imagine, the reality is that gas giants are not and never will be colonies for humanity. They're wonders to explore remotely, but not to inhabit. We need to set our sights on more feasible targets and leave the gas giants to the probes and our curiosity. The dream of living on a gas giant is just that, a dream. It's based on a misunderstanding of what these planets are. They're vast, beautiful, and mysterious, but they are not homes. They are laboratories for science, not backyards for children. So let's appreciate them for what they are and focus our colonization efforts where they have a chance of success. That's the pragmatic approach to space exploration. Remember, colonization requires a foundation, literally and figuratively. On gas giants, that foundation is absent, replaced by an endless gradient of gas and fluid. This isn't a matter of engineering prowess, it's a matter of physics. The materials we have, the energy we can harness, and the human body itself are not suited for such an environment. Even if we could create a floating habitat that survives for a while, it would be a precarious existence, constantly on the brink of disaster. The risks outweigh any potential benefits, especially when there are other celestial bodies more amenable to settlement. So, as we dream of spreading humanity across the solar system, let's keep our feet on the ground. or at least on something solid. Gas giants will continue to captivate our imagination, but they should remain in the realm of exploration, not colonization. That's the sobering truth about these magnificent planets. They teach us about the diversity of worlds, but they also teach us about our limits. And that's okay. Understanding our limits helps us channel our resources wisely. So let's leave the gas giants to the robots and the scientists, and focus on building a future where humans can truly thrive. Even if we could somehow solve the riddle of having no ground beneath us, the next force waiting for us is utterly inescapable and would reshape every aspect of existence: gravity. The gravity on a place like Jupiter is not just strong, it is a defining and ultimately crushing characteristic that makes the planet a prison, not a promise. First of all, let's clarify what we mean by gravity on a gas giant. Since there's no surface, we often refer to the gravity at the cloud tops, the 1 bar pressure level we talked about before. At that altitude on Jupiter, the gravitational pull is about 2.4 times stronger than Earth's. That means if you weighed 150 pounds on Earth, you'd feel like you weighed 360 pounds there. Just standing, or rather floating, would be an immense effort. Your bones, your muscles, your heart would be under constant, unrelenting strain. But here is the critical and terrifying part. That gravity figure is just the starting point. It is the gentlest it will ever be. As you descend into the atmosphere, the gravity does not decrease. In fact, it increases. This is because, while you're getting closer to the planet's mass concentrated at the core, the immense density of the material around you adds to the pull. We are not talking about a linear increase either. Deep inside Jupiter, the gravitational force becomes monstrous, many times greater than what we experience on Earth's surface. This single fact has devastating implications for any notion of colonization, and it touches everything from human health to the very nuts and bolts of construction. Let's start with the human body. We're exquisitely adapted to Earth's 1G environment. Our cardiovascular system pumps blood against that specific force. Our bones maintain density to support our weight, and our muscles are calibrated for it. In a sustained high-gravity environment, the body begins to struggle almost immediately. On Jupiter, even at the cloud tops, simple movement would be exhausting. The heart would have to work much harder to circulate blood, particularly to the brain, leading to a high risk of fainting or cardiovascular failure over time. The skeletal system would bear a much heavier load, which might sound like it could lead to stronger bones, but in reality it more likely leads to joint damage, spinal compression, and a higher propensity for fractures from minor stresses. Muscle fatigue would be constant, turning everyday tasks into Herculean efforts. The long-term physiological effects are not fully known, because we have never sustained humans in such an environment, but they would undoubtedly include severe degeneration, chronic pain, and a drastically reduced lifespan. Life would be lived in slow motion, under a perpetual heavy blanket. But the human body is only part of the problem. The structures we would need to live in would face an engineering nightmare. On Earth, our buildings are designed to handle 1G of downward force and some lateral forces from wind or seismic activity. On Jupiter, the primary downward force from gravity is more than double at the entry point, and climbs from there. Every single component of a habitat, from the largest structural beam to the smallest bolt, would need to be engineered to withstand that relentless pull. This isn't just about making things thicker or stronger in a simple way. The stress is constant and pervasive. Consider a floating habitat. To stay buoyant at a certain level, it needs to maintain a specific volume and density. But the crushing gravity wants to compress everything. It would act to shrink that volume, increasing its density and causing it to sink. To counteract this, the structure must be unimaginably rigid to prevent deformation, or it must have active systems constantly adjusting buoyancy, which consumes vast energy. The weight of the habitat itself, multiplied by the local gravity, becomes a key design constraint. The materials we take for granted, like steel and titanium, have a certain tensile strength, a point at which they bend or snap under a load. Under Jovian gravity, especially deeper down, common aerospace materials would fail. We would need to invent entirely new alloys or composites with strength-to-weight ratios that are currently the stuff of science fiction. And even if we built such a structure, the gravity would impose a brutal toll through a process called fatigue. Metal under constant stress, even if it is below its breaking point, can develop microscopic cracks that grow over time. The unending gravity combined with the turbulence of the atmosphere would accelerate this fatigue immensely. A habitat might have a safe operational lifespan of mere years before critical components need replacement, a maintenance task that would be perilous in the extreme. Furthermore, gravity dictates the energy cost of everything, especially movement. Within the habitat, elevators between decks would need to be incredibly powerful. Any machinery would have to be built to operate under the increased load. But the most profound energy trap is escape. Gravity creates what physicists call a deep potential well. Falling into it is easy, climbing out is extraordinarily hard. This is the fundamental challenge of leaving any massive body, but for gas giants it is particularly severe because there is no surface from which to launch. Let's say a supply ship or a crew transfer vehicle needs to reach a colony floating deep in the atmosphere. First, it must perform a brutal atmospheric entry to get down there, shedding enormous kinetic energy as heat. But then, to leave, it must claw its way back out. To reach orbit from Earth, a rocket needs to achieve a velocity of about 5 miles per second. To achieve orbit from Jupiter, starting from the cloud tops, you need to reach a velocity of over 30 miles per second. That is 6 times the delta V required, and the rocket equation is exponential, not linear. The fuel required becomes astronomically, pun intended, large. For every pound of payload you want to lift from Jupiter's cloud tops, you might need hundreds or thousands of pounds of fuel. And remember, this is from the cloud tops. If your colony is floating deeper to achieve buoyancy, the situation is far worse. You're starting from deeper in the gravity well, so you need even more fuel to climb up to the cloud tops before you can even think about orbit. This makes the concept of regular resupply or personnel rotation a practical impossibility. The colony would be isolated, a life sentence. The ships that brought the initial colonists and materials would likely be dismantled for parts, because they could never carry enough fuel for a return trip. This turns the colonization effort from an expansion into exile. The gravity well also affects internal atmospheric processes that would impact a colony. The immense gravity is the engine behind the planet's stupendous weather. It drives the convection that creates the powerful jet streams and the eternal storms. A floating habitat would not be sitting in a calm sea but in a raging river. The gravity pulls the atmospheric gases down with such force that it creates layers of differential rotation and shear that manifest as those colourful bands. A habitat would need to navigate or withstand these currents, and the energy required to maintain station against a several 100-mile-per-hour wind under 2.4 Gs is again a colossal challenge. Every action is amplified, every force is multiplied. Now think about something as simple as a structural repair, sending an engineer outside in a suit to fix a damaged panel. On the International Space Station, an astronaut's suit is bulky but manageable in microgravity. On Mars, a suit would be heavier, but the gravity is only about 1/3 of Earth's. On Jupiter, a suit capable of withstanding the external pressure and chemistry would already be a massive rigid contraption. Then you add the effect of gravity. Moving that suit, lifting an arm, turning a wrench would require immense strength from the occupant and likely powered exoskeletal assists. The risk of a fall is meaningless because you're floating, but the risk of being carried away by the wind or being unable to move against the gravitational pull is very real. The environment is actively working against every single human endeavour, and gravity is the chief architect of that hostility. It also has subtler effects. The distribution of gases in the atmosphere is stratified by gravity, with heavier molecules sinking. This could concentrate toxic chemicals like ammonia or hydrogen sulfide at certain depths, precisely where a habitat might need to float for buoyancy. Gravity is not just pulling on you, it is organising the entire poisonous environment around you. In science fiction, artificial gravity is often a solved problem, a switch you flip on a starship. But generating artificial gravity, especially to counteract real gravity, is not about creating a force, it is about creating an acceleration. The only practical way we know to simulate gravity is through rotation, creating a centripetal force that pushes you against the outer wall. But how do you spin a habitat to create a comfortable 1G when the real gravity outside is 2.4 Gs and trying to pull you straight down? You would have to spin it fast enough to create a total apparent gravity of 1G, but the vectors would be strange and disorienting, combining the linear pull of the planet with the rotational pull of the habitat. The engineering complexity is mind-boggling, and any failure of the spin mechanism would immediately subject everyone to the full crushing weight of the planet. Ultimately, gravity is the ultimate deal breaker. The lack of a surface is a conceptual problem, but gravity is a physical, mathematical, and physiological barrier written in the fundamental laws of the universe. It defines the energy cost of every action, it limits the materials we can use, it destroys the human body over time, and it locks anything that enters into a permanent trap. We can perhaps imagine robots or AI systems built to withstand high G-forces for limited missions, but for fragile human beings to live, work, raise families, and build a society under such conditions is not just impractical, it is a form of torture. The planet's gravity is not a parameter to be worked around. It is the central, overwhelming reality of the place. It is the reason Jupiter can hold on to its enormous atmosphere of light gases. It is the reason its interior is crushed into exotic states of matter. And it is the reason that, for us, it will forever remain a brilliant jewel in the sky to be observed from a very, very safe distance. Our bodies and our technology are born of a gentler world, and the gravitational might of a gas giant is a force that reminds us of our place in the cosmos. We are creatures of a small rocky planet, and the kingdoms of the giants are not for us. They are realms of pressure and force that dwarf our understanding and defy our aspirations for a foothold. So, while we might send probes on one-way trips into the abyss to satisfy our curiosity, we must understand that for human life, that gravitational force is not a welcome. It is a perpetual and crushing rejection. So gravity sets the stage, creating this immense downward pull that shapes everything. But that force translates into something even more immediately destructive as you venture deeper, the atmospheric pressure. This isn't just high pressure like the bottom of our ocean. This is pressure on a scale that completely defies human intuition, a scale where the very concepts of solid and liquid lose their familiar meaning. To survive on Earth, we live under a comfortable blanket of air that exerts about 14.7 pounds per square inch, which we call 1 atmosphere. In the deepest ocean trench, the pressure reaches a little over 1,000 atmospheres, which is crushing, but we have built submersibles that can briefly visit those depths. On a gas giant, those numbers stop being numbers and start sounding like fantasy. As you descend from the cloud tops of Jupiter, the pressure doesn't just increase, it skyrockets exponentially. Within just a few hundred kilometers down, you'd experience pressures thousands of times greater than Earth's sea level. Go deeper, and you quickly reach millions of atmospheres. Let that sink in for a moment. Not thousands, but millions. At these levels, pressure ceases to be a mere environmental condition and becomes the primary architect of reality, overriding the normal rules of chemistry and physics. What does that mean for a hypothetical colony? It means that any structure, no matter how robust, would face an environment that treats our strongest materials like tissue paper. Think of the strongest submarine ever built, with hulls of thick titanium steel. On Earth, it's designed to resist the immense pressure of the deep ocean by having an internal pressure of 1 atmosphere pushing out against the external water pressure pushing in. The differential might be 1,000 atmospheres. On Jupiter, at depths where the atmosphere might be dense enough to consider floating a habitat, the pressure differential wouldn't be 1,000. It could be tens or hundreds of thousands of atmospheres. There's no material known to humanity, no alloy, no composite, no diamond nanofiber that could withstand that kind of static, unrelenting force without instantaneous implosion. The hull wouldn't just buckle or leak, it would be compressed into a tiny, dense sphere in a fraction of a second. The engineering challenge isn't about making something strong enough, it's that the required strength exceeds the fundamental atomic bonds of matter as we know it. We can look at what happened to the Galileo probe for a sobering real-world example. That probe was our most rugged atmospheric entry vehicle, a technological marvel. It entered Jupiter's atmosphere in 1995, protected by a heat shield that withstood temperatures of around 15,000 degrees Celsius. But its mission wasn't to survive, it was to transmit data for as long as possible on the way down. It lasted about an hour, descending a mere 150 kilometers or so into the atmosphere before the pressure and temperature destroyed it. The pressure that killed it was around 23 times Earth's atmospheric pressure, and the temperature was about 150 degrees Celsius. That's nothing. That's a shallow dive. It didn't even get to the interesting, horrifying part. It was snuffed out while still in the comparatively tame upper layers. For a colony, you'd need to go much, much deeper to find the density required for buoyancy, plunging into realms where the pressure is not tens, but hundreds of thousands of atmospheres. The pressure is so immense that it fundamentally changes the state of matter itself. Deep within Jupiter, scientists believe hydrogen, the lightest element, undergoes a profound transformation. Under the weight of millions of atmospheres, the hydrogen molecules are squeezed so tightly together that they break down. The electrons are ripped from their atoms, forming a strange fluid sea of electrically conductive material called liquid metallic hydrogen. This isn't a theoretical state we can easily recreate. It's the condition that exists in the interior of Jupiter, a form of matter that is more extreme than the core of our own planet. The pressure required to create this is staggering, but it illustrates the point. To reach any kind of stable floating point in the atmosphere, a habitat might need to sit at a depth where pressures are a significant fraction of that transition. Even if we could build a magic bubble that could withstand it, what would be outside? Not a gas, not a liquid as we know it, but a supercritical fluid, a hellish soup with properties of both, seething with heat and turbulence. And pressure isn't a constant, gentle squeeze. The atmosphere of a gas giant is dynamic, with unimaginably powerful currents and convection. A habitat would need to withstand not just the static pressure trying to crush it uniformly, but also dynamic pressure variations from these flows. A sudden downdraft or an encounter with a turbulent eddy could create a momentary spike in pressure on one side of the structure, a differential that would be more than enough to tear it apart. It would be like sitting in a submarine that's also inside a hydraulic press that's being randomly hammered from different sides. The concept of a hull becomes almost laughable. To resist external pressure, a vessel needs to be internally pressurized itself. Our habitats in space are pressurized to Earth normal, about 1 atmosphere. The difference between inside and outside in space is 1 atmosphere, with the inside pushing out. On a gas giant at depth, the outside is pushing in with a force of perhaps 100,000 atmospheres. Your habitat's interior pressure of 1 atmosphere is a rounding error, completely irrelevant. The structure's integrity would rely solely on the material's ability to resist being crushed by that external force, with no helpful internal pressure to balance it out. You couldn't even use the classic submarine design principle of a spherical pressure hull because the scales involved make any known material fail. People sometimes suggest active support structures, using powerful magnetic fields or some other futuristic technology to hold the pressure at bay. But containing magnetic fields of that magnitude, or generating repulsive forces against physical pressure, would require energy levels that are themselves fantastical and would generate enormous amounts of heat, compounding the already insurmountable thermal problem. It's a vicious cycle with no solution. Let's consider the sheer weight of the column of atmosphere above you. On Earth, at sea level, you have about 60 miles of atmosphere above you, and it weighs about 14.7 pounds per square inch. On Jupiter, the atmosphere is thousands of miles deep, and it's composed of much denser material as you go down. The weight of that column is what creates the pressure. At a depth where the pressure is 100,000 atmospheres, every single square inch of your habitat surface is supporting a weight equivalent to 100,000 times the entire Earth's atmosphere stacked on top of it. To put it in a more visual way, it's like having a mountain range made of lead standing on every postage stamp-sized area of your walls. No known structure, no arcology, no fortress could bear that load. The pressure also affects everything you try to do. Any moving part that needs to interface with the outside environment, like a sampling port or a docking hatch, becomes a single point of catastrophic failure. The seals required to hold back that kind of pressure don't exist. Even if you could create them, the act of opening such a port would be like trying to open a door against a tsunami. Any tiny leak wouldn't be a hiss of air. It would be an instantaneous hypersonic jet of super dense fluid that would cut through metal like a plasma torch and flood the interior in milliseconds. Maintenance and repair outside the habitat are concepts that cease to have meaning. You couldn't send an EVA suit out not only because of the heat and chemistry, but because the suit itself would be crumpled into a ball the moment it was exposed to the external pressure. Robotics would fare no better, unless they were built to the same impossible standard as the main habitat, which makes them too massive and power-intensive to be practical. Furthermore, this immense pressure has a direct relationship with the gravity we just discussed. It is the gravity that creates the pressure. The relentless pull of the planet's mass compresses the lower atmosphere, packing the molecules together more and more tightly. So you cannot escape one by solving the other. They're two sides of the same coin. Attempting to float higher to reduce pressure means dealing with lower atmospheric density, which makes buoyancy harder to achieve and exposes you to more severe radiation and colder temperatures, while still leaving you in a pressure regime that is likely fatal to any structure over time. There's no safe zone, no Goldilocks region where the pressure is just right for human-scale engineering. The windows we see in sci-fi movies offering panoramic views of swirling clouds are pure fantasy. A window is a structural weakness, a discontinuity in the hull material. At these pressures, even the thickest transparent aluminum or diamond pane would shatter or flow like plastic. The viewport would need to be tiny, incredibly thick, and would likely become opaque due to stress distortions. The colonists would live in a completely sensor-driven world, seeing the outside only through cameras that themselves would need to be housed in impossibly strong enclosures. The psychological weight of knowing that a wall a few feet thick is all that separates you from being instantly compressed into a speck would be unbearable. The pressure also influences the very gases you're floating in. At extreme pressures, gases behave in non-ideal ways. They can become solvents for materials that are inert at lower pressures. The supercritical fluid mixture of hydrogen, helium, and other volatiles could start to infiltrate microscopic pores in the hull material, leading to a form of high-pressure corrosion or embrittlement that we can't even model accurately. Your habitat's walls might slowly become saturated with the planetary atmosphere, weakening them from the inside out. In essence, the atmospheric pressure of a gas giant is not an obstacle. It is a flat-out declaration that certain volumes of space are off-limits to complex structures. It is a fundamental property that defines the planet's interior as a realm accessible only to theory and indirect measurement. We can send sturdy probes on suicide missions to gather data for an hour, but building a permanent home there is akin to building a house out of glass at the bottom of the Mariana Trench, and then expecting it to withstand earthquakes. The forces involved are so far beyond our engineering paradigm that they might as well be magical. We are creatures of a low-pressure environment. Our technology, from the rivets in a ship to the seals in the engine, is born from and for a world of gentle pressures. The gas giant does not operate on that scale. It operates on a scale where matter is remade, where the rules are written by the collective weight of a world. To imagine colonizing it is to imagine defeating pressure itself, not in a laboratory for a fleeting moment, but continuously, across a vast structure for generations. That is a fight where physics holds all the cards, and it is a fight we cannot win. The pressure is an absolute, unforgiving barrier, more effective than any force field in keeping us out. It silently and perpetually enforces the rule that some places in the universe are for looking at, not for living in. Our curiosity can send robotic emissaries to their doom to bring back knowledge, but our bodies and our homes will forever be confined to the gentle, thin skins of rocky worlds, where the sky is above us and the ground, solid and reliable, is firmly beneath our feet. The immense pressure of a gas giant is the ultimate expression of that world's otherness. A constant, crushing reminder that we are not welcome in its depths. If the pressure is the silent, crushing vice, then the heat is the roaring, omnipresent furnace that comes with it. We are not just talking about a bit of warmth. We are talking about a fundamental and inextinguishable inferno generated from within the planet itself, creating a thermal environment that is as hostile as the pressure is absolute. On Earth, our primary source of heat is the sun, and we are very good at managing that. We have an atmosphere that moderates temperature, and we can insulate ourselves from the cold of space or the heat of the day. A gas giant operates on a completely different principle. While it does receive some heat from the sun, that is a trivial contributor compared to the internal heat generated by the planet's own massive bulk and ongoing physical processes. This internal heat is the engine that drives the monstrous weather, and it creates a temperature gradient that climbs from frigid cold at the cloud tops to temperatures hotter than the surface of the sun in the deep interior. For a colony, this presents a cooling problem of literally astronomical proportions. Let's break down where this heat comes from. First, there is primordial heat left over from the planet's formation. When Jupiter collapsed from a cloud of gas and dust billions of years ago, the potential energy of all of that material falling inward was converted into an enormous amount of heat. That heat has been slowly leaking out over the eons, but because the planet is so vast, the process is far from over. Second, and more significantly, there's ongoing gravitational contraction. Jupiter is still not a perfectly stable static sphere. It is very, very slowly shrinking under its own weight. This infinitesimal contraction, maybe a few centimeters per year, releases a staggering amount of gravitational potential energy, which is converted directly into heat. This is like a constant planet-sized internal engine. Third, there may be heat released from the differentiation and settling of heavier elements towards the core, and from other processes like the decay of radioactive elements, though that is a smaller factor compared to the gravitational sources. The result is that Jupiter radiates almost twice as much energy into space as it receives from the Sun. It is a giant self-heating world. Now, what does this mean for temperatures as you descend? At the cloud tops, where the pressure is about 1 bar, the temperature is shockingly cold, around minus 145 degrees Celsius. That's manageable with insulation, but you can't stay there because of buoyancy and radiation issues. As you go down, hoping to find a stable density layer for your habitat, the temperature rises, not gradually, but steadily and relentlessly. Data from probes and models suggest that at a depth where the pressure is about 10 times Earth's, the temperature might be around 20 degrees Celsius, a seemingly comfortable room temperature. This is the depth that sometimes gets mentioned in speculative articles as a possible habitable zone. But here's the kicker. That is a snapshot in a steep thermal gradient. You're not sitting in a cozy, stable layer of air at room temperature. You're perched on a thermal cliff. Below you, the temperature soars. Above you, it plummets. Your habitat is a tiny bubble of carefully regulated environment in the middle of an extreme and violent energy flow. The planet is trying to move heat from its incredibly hot interior out to space, and your colony is sitting right in that pipeline. The engineering challenge is not heating your habitat, it is getting rid of heat, and doing so in an environment that is already fiercely hot. Let's say you manage to build a magical structure that can withstand the pressure at a depth where the ambient external temperature is a balmy 50 degrees Celsius. Your habitat with people, computers, life support and machinery generates its own internal heat. On the International Space Station, getting rid of waste heat is a major issue, and it does so using massive radiator panels that dump infrared radiation into the cold vacuum of space. In the depths of a gas giant, you have no cold vacuum. You're immersed in a dense hot fluid. You cannot radiate heat away effectively because the surrounding medium is already hot, and radiation is inefficient in such an atmosphere. You cannot simply vent hot air or use convective cooling with the outside, because the outside is hotter than you want your inside to be. You would need to actively cool your habitat, pumping heat from a cooler interior to a hotter exterior, which is a thermodynamic uphill battle. This requires monstrous amounts of energy and a cooling system of unimaginable scale and efficiency. It's like trying to keep a refrigerator cold by opening its door inside a burning building and expecting that to work. The heat pumps and radiators would have to be colossal, and they themselves would generate more waste heat, creating a vicious cycle. The temperature gradient itself is a deadly hazard. Any breach in the habitat's hull, any tiny leak or crack, wouldn't just let in gas, it would let in a blast furnace. The heat transfer would be so rapid that the interior would flash to deadly temperatures almost instantly. The thermal stress on materials is another nightmare. Different parts of the structure would be at different temperatures, causing expansion and contraction that could fatigue and crack even super strong materials over time. Now let's talk about going deeper, which you might be forced to do for buoyancy or resource reasons. The temperature does not plateau, it keeps climbing. At the depth where hydrogen begins its transition to liquid metallic hydrogen, temperatures are estimated to be many thousands of degrees Celsius, perhaps as high as 10,000 degrees. That is hotter than the surface of the Sun. This is not an environment, it is a continuous nuclear fusion experiment without the fusion. The heat is so intense that it actively shapes the planet's structure and is the primary driver of its convective storms. The Great Red Spot and the powerful jet streams are fueled by this internal heat engine. So, your floating habitat isn't just sitting in a hot bath, it's sitting in the middle of a planet-sized, heat-driven storm system. The convection currents that carry heat from the interior to the upper atmosphere are violent and turbulent. These are not gentle breezes, they are the planetary equivalent of the rolling boil in a pot of water, but scaled to a size larger than Earth itself. This brings us to another critical point. The heat directly enables the other horrors we've discussed. The high temperatures contribute to the incredible pressure by increasing the kinetic energy of the gas molecules. They power the winds that would tear a habitat apart. They create the conditions for exotic chemistry and electrical storms of staggering proportions. The internal heat is the reason the planet is a dynamic, seething cauldron and not a cold, static ball of gas. You cannot isolate the heat problem from the pressure problem or the wind problem. They are all intertwined consequences of the planet's fundamental nature. Consider the energy budget for a colony. On a place like Mars, you might worry about generating enough heat to survive. On a gas giant, your entire energy infrastructure would be devoted to running a cooling system. Your power source, likely nuclear, would have to be immense just to pump heat out of your living spaces into an environment that is already hostilely hot. The waste heat from your power plant itself becomes a major liability, requiring even more cooling capacity. It's an exponentially difficult problem. There is no radiating to space as a solution. You're buried under thousands of miles of opaque, dense atmosphere. The only way to dump heat is into that atmosphere, which means you have to make your habitat's exterior even hotter than the already hot surroundings to create a temperature gradient that drives heat flow away from you. But making your hull hotter weakens its materials, accelerates corrosion, and makes any accidental contact with it instantly lethal. It's a no-win scenario. Furthermore, the internal heat of the planet is not uniform or predictable. There could be plumes of hotter material rising from the depths, local variations that could suddenly increase the ambient temperature around a habitat by hundreds of degrees. There is no weather forecast that could reliably predict this. It would be a random event that could cook a colony in its shell. The thermal inertia of the planet is so vast that no human-scale intervention could ever hope to modify the local environment. You are at the complete mercy of planetary physics. In science fiction, heat is often hand-waved away with thermal shields or coolant systems. But the scale here is planetary. You're not dealing with the heat from re-entry lasting a few minutes. You're dealing with the total thermal output of a giant world applied continuously, forever, on all sides of your structure. It is an unending omnidirectional assault. The concept of a heat sink disappears because everything is already hot. Even if you could use some of the atmospheric gases in a cooling cycle, you'd be trying to use a hot fluid to cool a hotter system, which is thermodynamically backwards. The sheer mass of heat that needs to be moved is incomprehensible for any technology we can envision, even in a distant future. Our entire industrial civilization on Earth relies on using cold sinks, the atmosphere or the ocean, to dump waste heat. A gas giant offers no such sink, only a hotter neighbour. This makes sustained, closed-loop human habitation a physical impossibility, not an engineering difficulty. It violates the basic principles of thermodynamics we rely on for every cooling system we've ever built. So while the crushing pressure might instantly destroy a habitat, the heat would ensure that even a pressure-proof habitat becomes an inescapable oven. It is the slow, sure guarantee of failure. The internal heat of a gas giant is the final, definitive argument against colonization. It is the reason these worlds glow in the infrared, the engine of their beauty and their fury. We can admire that from afar as we admire the sun, but we can never touch it, never live within it. Our bodies and our machines are calibrated for a narrow thermal band, a tiny sliver of the universe's temperature range. The gas giant exists far, far outside that sliver, in a realm of energy where matter is remade and the very idea of comfortable is meaningless. It is a reminder that the universe is not only mostly empty, but where it is not empty, it is often violently incandescently energetic in ways that preclude our delicate form of life. To dream of colonizing such a place is to misunderstand the fundamental nature of heat, energy, and our own profound thermal fragility. We are children of a temperate world, and the infernos of the giants are not for us. They are cosmic landmarks, forever beyond our reach, their heat a barrier more effective than any wall. That internal heat we just talked about doesn't just make things hot, it sets the entire atmosphere into motion on a scale that makes our worst hurricanes look like a gentle breeze. This is the realm of the hypercanic winds, eternal tempests and chaotic turbulence that would shred any notion of a stable colony. When you look at Jupiter, those beautiful bands of orange, white and brown are not just clouds, they are the visible tops of planet-wide jet streams, rivers of gas moving at speeds that defy belief. These winds are not weather as we know it. They are the permanent, ingrained climate of a giant, and they represent a force of nature so vast that anchoring against them is impossible. The numbers are hard to grasp. On Earth, A Category 5 hurricane has sustained winds of about 157 miles per hour or more. That's a devastating force that can level towns. On Jupiter, the jet streams routinely exceed 350 miles per hour, with some estimates pushing over 400 miles per hour. And these are not temporary storms, these are permanent features, flowing in alternating east-west directions, sustained for decades, centuries, or even millennia by the planet's internal heat and rapid rotation. A floating habitat would be inserted into these flows, and it would have no anchor, no brake, and no safe harbour. It would be carried around the planet at these horrific speeds, a helpless passenger on a ride that never ends. But speed is only part of the terror. The real structural killer is the shear. Those beautiful bands are adjacent to each other, and often they are moving in opposite directions or at vastly different speeds. The boundary between a westward flowing jet and an eastward flowing jet is a zone of extreme wind shear. If you imagine a habitat that is large enough to be a colony, perhaps a few kilometres across, one side of it could be in a stream moving east at 300 miles per hour, while the other side is in a stream moving west at 200 miles per hour. That is a 500 mile per hour difference across the structure. The shear forces would literally tear it apart, stretching and ripping it like paper in a child's hands. No material could withstand that kind of differential stress for long, so a colony would have to be incredibly compact and strong, or it would have to somehow magically stay entirely within a single uniform stream, which is impossible given the turbulent and dynamic nature of these atmospheric rivers. Then there are the storms themselves, the most famous being Jupiter's Great Red Spot. That spot is not a surface feature, it is a colossal atmospheric vortex, an anticyclone larger than the entire planet Earth. It has been raging for at least 350 years, possibly much longer. The winds on its periphery are those 400 mile per hour monsters, spinning around a relatively calm centre. It is a permanent hurricane that could swallow our world whole, and there are countless other, smaller storms, vortices and disturbances constantly churning the atmosphere. A colony could be formed, and within a year find itself on a collision course with a storm system that has existed since before the invention of the telescope. There is no forecasting this with any long-term accuracy because the system is too complex and too energetic. You're living inside the weather, not observing it from space, so your warning time for a catastrophic encounter could be days or hours. The turbulence at these scales and speeds is another insurmountable problem. Turbulence isn't just bumpy air, it is a chaotic multi-scale phenomenon that transfers energy from large movements down to smaller and smaller eddies. For a habitat, this means constant, random buffeting and vibration. Imagine being inside a giant aluminum can that is being shaken violently and incessantly, day after day, year after year. This vibrational loading would cause metal fatigue at an accelerated rate, leading to cracks in welds, failures in structural joints, and the eventual disintegration of the habitat from the inside out. Every system, from life support pipes to electrical conduits, would have to be designed to withstand this perpetual shaking, which adds immense weight and complexity. And let's be clear, this is not occasional turbulence like an airplane hitting an air pocket. This is a constant, brutal, and unpredictable pummeling from a fluid that, at those depths, may have the density of water, but is moving at speeds impossible in any earthly ocean. The energy contained in these winds is mind-boggling. It is the kinetic expression of the planet's internal heat engine. To resist being moved by them, to maintain a stationary position relative to the planet's interior or to another colony, would require an equal and opposite application of force. In other words, you would need thrusters or propellers or some kind of propulsion system running continuously, 24 hours a day, 7 days a week, forever, just to keep your habitat from being swept away at hundreds of miles per hour. The fuel or energy requirement for that is infinite for all practical purposes. You cannot carry enough fuel, and even a nuclear reactor would eventually run out of fissile material trying to power such a Sisyphean task. So you must go with the flow, but going with the flow means you have no control over your location. You're adrift on a planet-wide conveyor belt. This makes any concept of multiple colonies or a settled community absurd. How would you travel between two colonies if they are in different jet streams moving in opposite directions? The relative speed between them could be 700 miles per hour or more. A shuttle trying to go from one to the other would face a headwind or crosswind of unimaginable force, requiring even more fuel. And if you're all drifting, you might start on the same longitude, but end up scattered around the planet in a matter of days or weeks. There is no there. You cannot map coordinates on a gas giant's atmosphere in any meaningful, stable way for human settlement. The winds also interact with other deadly factors. They carry with them particles of ammonia ice, water ice, and other compounds that, at several hundred miles per hour, act like sandblasting grit against any exterior surface. The abrasion would slowly erode the hull, cloud cameras and sensors, and clog any external moving parts. Furthermore, these high-speed winds are coupled with the immense pressure and temperature gradients. A sudden downdraft or updraft could plunge or lift a habitat thousands of meters in a short time, subjecting it to rapid changes in ambient pressure and temperature that could overwhelm its systems. It would be a constant, desperate struggle for stability in an environment designed for perpetual, violent motion. Think about the psychological impact. On a rocky planet, even with bad weather, there is a solid, unmoving reference point, the ground. In this environment, everything is in motion. The sky outside your window, if you had one, would be a frenetic, streaking panorama of clouds racing by at impossible speeds. The sense of vertigo and disorientation would be profound and unending. There would be no calm days, no still nights. The constant roar of the wind against the hull, even dampened by the structure, would be a reminder of the fury outside. The knowledge that your entire world is hurtling through an alien sky at the speed of a fighter jet, with no way to stop, would be a unique and terrible form of anxiety. From an engineering perspective, we have no analogues for building in such an environment. Our tallest skyscrapers are designed to sway in the wind, but they are anchored to bedrock. Our ships are designed to handle ocean currents and storms. They can seek shelter, or are built with the understanding that the ocean surface is a fluid of relatively consistent density. In the deep atmosphere of a gas giant, the fluid changes density, pressure and temperature dramatically with altitude, and the wind speeds are orders of magnitude greater. We cannot even test materials or designs for this in wind tunnels on Earth, because we cannot recreate the combination of density, composition and velocity. Any design would be a blind guess, almost certain to fail. The hypercanic winds are the final piece of the atmospheric trifecta of doom, alongside crushing pressure and hellish heat. They are the dynamic, kinetic proof that a gas giant is not a place, but a process, a continuous violent reaction. You cannot build a home inside a process. You can only observe it. The winds ensure that even if you solve the pressure and heat problems with some miracle material, your colony would be reduced to scrap metal by the sheer, unrelenting force of motion. They turn the entire planet into a maelstrom, a blender operating on a planetary scale. Colonization requires stability, a foundation, and a predictable environment. The winds of a gas giant offer the exact opposite: chaos, perpetual motion, and unimaginable force. They are the atmosphere's answer to the question of colonization, a roaring, endless no written in jet streams and storms that last for centuries. Our future in space lies on quiet, solid grounds, where the wind, if it blows at all, is a gentle whisper, not a perpetual, planet-encircling scream. Even if you could design a vessel to withstand the pressure, reinforce it against the heat, and shape it to somehow navigate those eternal winds, you would then face an invisible and utterly lethal barrier that permeates the space around a gas giant like Jupiter radiation. This is not ordinary background radiation. This is a concentrated, intense and perpetual onslaught of high-energy particles that would fry electronics and kill living tissue in a very short time. Jupiter possesses the most powerful planetary magnetic field in our entire solar system, a magnetosphere so vast that if it were visible to the naked eye, it would appear larger than the full moon in our sky. This magnetic field is generated by the churning, electrically conductive layer of liquid metallic hydrogen deep in Jupiter's interior, acting like a colossal dynamo. This field is a double-edged sword. It's fascinating for science, but for colonization, it's a death sentence. The field captures and accelerates charged particles, primarily electrons and protons from the solar wind, trapping them in intense radiation belts that are millions of times more powerful than Earth's Van Allen belts. These belts form a donut-shaped region of extreme radiation around the planet, and anything, whether a spacecraft or a floating colony, that spends any time within these zones will be subjected to a continuous penetrating hail of atomic destruction. Let's talk about what this radiation does. These are not simple particles, they're accelerated to nearly the speed of light. giving them enormous energy. When they strike matter, they don't just bounce off, they smash into atomic nuclei, break molecular bonds, and create cascades of secondary particles. For electronics, this is a nightmare. It causes what engineers call single event effects, where a single particle can flip at the memory bit, causing a computer to glitch or crash. More severely, it can cause latch-up, permanently damaging a microchip. Over time, the cumulative dose degrades semiconductors, damages solar panels, and darkens lenses and windows. For a colony reliant on complex automated life support and navigation systems, radiation-induced failures would be constant and catastrophic. You couldn't just reboot, the hardware itself would be physically damaged. For humans, the effects are biologically devastating. This kind of high-energy particle radiation is ionizing radiation, meaning it has enough energy to knock electrons out of atoms in your body's cells, damaging DNA and other critical cellular structures. Acute exposure leads to radiation sickness, with symptoms like nausea, vomiting, hair loss, and destruction of bone marrow, leading to infection and hemorrhage. A short, unshielded exposure in Jupiter's main radiation belts would deliver a lethal dose in minutes. Chronic, lower-level exposure, even inside a partially shielded habitat, dramatically increases the risk of cancer, cataracts, and can cause damage to the central nervous system and heart. It also poses a severe threat to reproduction and fetal development. Essentially, the radiation environment around Jupiter is instantly and permanently hostile to carbon-based life. Now, how do you shield against this? On Earth and in low Earth orbit, our atmosphere and planet's magnetic field provide a protective bubble. On a gas giant, you're inside the source of the radiation, not outside it. Shielding requires mass. To attenuate this kind of high-energy particle radiation, you need dense materials like lead, concrete or water. Estimates suggest that to bring radiation down to safe levels for long-term human habitation, you might need a shielding shell several meters thick of water, or equivalent material around the entire living quarters. Let's think about what that means for a floating habitat. You're already struggling with buoyancy, pressure and heat. Now you need to encase your colony in a layer of water, or lead, that is multiple meters thick on all sides. The mass of this shielding would be astronomical, making the habitat impossibly heavy, sinking it instantly to depths where pressure and heat are even more extreme. It's a paradox. To be safe from radiation, you need to be deep and heavily shielded, but being deep exposes you to pressure and heat that will kill you. There is no altitude where you avoid all these threats, you trade one for another. The Juno spacecraft provides a perfect case study in the sheer difficulty of operating in this environment. Juno's mission designers knew the radiation was a showstopper. Their solution was to give Juno a highly elliptical polar orbit that skims close to the planet and then swings far out, minimizing time in the most intense radiation regions. More crucially, they placed Juno's most sensitive electronics inside a titanium vault, a shielded box about the size of a car trunk, with walls about a centimetre thick of solid titanium. This vault weighs about 200 kilograms. That's for a robotic spacecraft. Scaling that protection up to an entire habitat for hundreds or thousands of people is simply not feasible. The mass of titanium required would be greater than that of the largest skyscrapers on Earth. And even with that, Juno's instruments and systems are still degrading over time due to radiation exposure, and its mission lifespan is limited by this factor. A colony cannot have a limited lifespan measured in years. It needs to last for generations. The radiation also makes any concept of extravehicular activity, spacewalks or external repairs, utterly impossible. No spacesuit could provide adequate shielding. An astronaut venturing outside, even for a few minutes, would receive a fatal dose. All maintenance would have to be conducted by robots, which themselves would need to be heavily shielded and would still suffer rapid degradation. This means your colony's external integrity, its sensors, its propulsion for station keeping, all the things that keep it alive in that hellish atmosphere, would be failing constantly and could not be easily repaired. Furthermore, this radiation isn't a static shell, it's dynamic and influenced by solar activity. When the Sun has a coronal mass ejection or a period of high activity, the influx of particles can intensify Jupiter's radiation belts dramatically, creating sudden and severe radiation storms. Your colony would need to be designed for these peak events, not just the average already lethal background. This necessitates even more shielding, making the mass problem worse. There's also the secondary radiation problem. When high-energy particles strike the hull or shielding material, it can produce a shower of secondary particles like neutrons and gamma rays, which can be just as damaging. So your thick water or lead shield, while stopping the primary particles, itself becomes a source of secondary radiation that you must also account for. The engineering becomes a nightmarish series of trade-offs with no good outcome. Consider the psychological impact of this invisible threat. On a planet, you might fear storms or quakes, but you can see them coming. Radiation is silent, odorless, and invisible. You would be wholly dependent on dosimeters and monitoring equipment. A sensor failure could mean you wouldn't know you were being slowly poisoned until it was too late. The constant anxiety of living inside a machine that is constantly being bombarded and degraded, knowing that a breach in the shielding is as deadly as a breach in the pressure hull, would be a tremendous mental burden. The radiation belts also extend far out into space, creating a hazardous zone for approach and departure. Any shuttle traffic to and from the colony, already a near impossibility due to the gravity well, would have to plot courses that minimise radiation exposure, which further complicates the already insane flight dynamics. In essence, the radiation field of a gas giant like Jupiter is the ultimate deal-breaker, even more so than the atmospheric conditions in some ways, because it is so pervasive and penetrative. You can imagine, maybe with science fiction materials, building a structure that holds back pressure. You can imagine massive heat pumps. You can imagine aerodynamically sleek forms to handle wind. But radiation shielding is a brute force game of mass. There is no elegant force field, no magical energy barrier that can deflect these particles at the scale required. It comes down to putting mass between you and the radiation. And in the environment of a gas giant, mass is your enemy because mass sinks. It is the fundamental contradiction that cannot be resolved. To be light enough to float, you must be flimsy and vulnerable to radiation. To be safe from radiation, you must be so massive that you plunge to your doom. This is why robotic probes like Juno are the only viable explorers. They can be built with minimal focus shielding, sent on trajectories that minimise exposure, and are designed for a short, productive life. Humans are fragile, long-term creatures. We require safety for decades. Jupiter's magnetosphere does not allow for that. It is a natural particle accelerator of monstrous proportions, and it treats anything within its domain as merely target practice. So, while the clouds may swirl with beautiful violence and the planet may glow with internal heat, it is this invisible cage of radiation that truly seals its fate as a place forever beyond human reach. It is the final, definitive wall, proving that some of the universe's most magnificent sights are only to be observed from a very, very safe distance. Our future lies in the gentle, radiation-shielded environments of rocky worlds and sheltered space habitats, not within the deadly glow of a giant's heart. Beyond the invisible barrage of radiation lies the very substance of the planet itself, an atmosphere that isn't just unbreathable, but is actively chemically hostile to every aspect of human life and technology. We are not talking about an atmosphere like Mars, which is thin and mostly carbon dioxide, something we could theoretically process. We are talking about a thick, toxic soup where the most basic elements of our existence become lethal hazards. The air we breathe, 78% nitrogen and 21% oxygen, is a cosmic anomaly. The atmospheres of Jupiter and Saturn are composed overwhelmingly of hydrogen and helium, with trace amounts of methane, ammonia, hydrogen sulfide, and various hydrocarbons. This mixture is not just inert, it is a recipe for constant danger. To begin with, there is no oxygen. None. Not a single breathable molecule unless you bring it with you. Every litre of air in your habitat must be manufactured, recycled with near-perfect efficiency, or imported at stupendous cost. A leak is not just a loss of precious air, it is a potential catastrophe. If your oxygen-rich internal atmosphere leaks into the external hydrogen-rich environment, you have just created the perfect conditions for a massive explosion. Hydrogen and oxygen are famously energetic when combined, as anyone who remembers the Hindenburg can attest. A spark from an electrical panel, a static discharge, or even a hot surface could ignite the mixture, turning your habitat into a fireball. So your structure must not only hold pressure in, but it must also impeccably seal your internal chemistry from the external chemistry forever. The toxicity goes beyond just explosive combinations. Ammonia is a caustic, pungent gas that is highly irritating to eyes, skin, and the respiratory tract. Hydrogen sulfide is the smell of rotten eggs, a deadly poison that can paralyse the nervous system at high concentrations. These aren't just minor components, they're part of the cloud decks. In the zones where colourful ammonia ice clouds form, your habitat would be constantly exposed to this corrosive compound. It attacks many metals and plastics, degrading seals, wiring insulation, and sensor housings. Your external materials would need to be utterly resistant to chemical attack from a cocktail of reactive gases under immense pressure and temperature, a specification that eliminates most known aerospace materials. Then there is the issue of water. On Earth, water is a resource, a solvent, a necessity for life. In the upper atmospheres of gas giants, water exists primarily as ice crystals in clouds, but accessing it would be a monumental task. You would have to process colossal volumes of other gases to extract trace amounts of water vapour, an energy-intensive and inefficient process. In the deeper, hotter layers, water might be present in a superheated, supercritical state, completely inaccessible and mixed with everything else. You cannot simply drill a well or melt some ice. You would have to mine the sky itself with giant processing plants, all of which would face the same existential threats as the main colony. The sheer lack of familiar resources is staggering. There is no soil, no minerals, no ores. Everything needed to build, repair and sustain the colony must be brought from elsewhere. Every screw, every microchip, every sheet of metal, every litre of water, every nutrient for hydroponics. The logistical chain is not just expensive, it is an unbroken column of vulnerability stretching across hundreds of millions of miles of space. A single disruption, a missed shipment due to orbital mechanics or an accident, could doom the colony. This is not self-sufficiency, it is the most extreme form of dependency imaginable. The atmospheric chemistry also creates bizarre and dangerous weather phenomena beyond just wind. Lightning on Jupiter is thought to be hundreds of times more powerful than on Earth, and it likely occurs in clouds of ammonia and water, a different and potentially more conductive soup. Your floating metal habitat would be a prime lightning target in an eternal thunderstorm. Electrostatic discharges could fry external electronics constantly. Furthermore, the chemical mix can create exotic particles like diamond rain or helium rain deeper down. Fascinating to scientists, but representing yet another abrasive, unknown hazard for any structure. Consider the simple act of venturing outside. On Mars, you could design a suit that provides pressure and oxygen. On a gas giant, a suit would have to be a miniature submarine, resisting external pressure, heated or cooled against extreme temperatures, shielded against radiation, and now made of materials impervious to chemical corrosion from ammonia and hydrogen sulfide. It would be so massive and complex that mobility would be nearly impossible. Any joint or seal in the suit would be a point of failure where toxic gases could infiltrate. The concept of going outside for repair or exploration evaporates under the weight of these requirements. The internal chemistry of the colony becomes a closed, fragile bubble that must never interact with the outside. This places unbelievable strain on life support systems. Air revitalization must be flawless, recycling carbon dioxide and moisture and replenishing oxygen without loss. Waste processing must recover every possible atom of carbon, hydrogen, oxygen and nitrogen. Any chemical imbalance inside, perhaps from an off-gassing material or a malfunctioning lab, could poison the closed ecosystem. And all of this complex chemistry must operate perfectly under high gravity, constant vibration, and the threat of radiation-induced system failures. The psychological burden of living in such a chemically hostile environment is profound. On a submarine, sailors know the ocean outside is deadly, but it is largely water, a uniform medium. In a gas giant colony, the outside is a reactive, poisonous, explosive mixture. The smell of a leak might not be a neutral gas, it might be the sweet smell of ethylene or the rotten egg stench of hydrogen sulfide, a warning of immediate death. The fear of chemical contamination would be ever present, affecting morale and mental health. There is also the problem of waste disposal. You cannot dump anything overboard. Any waste product, if exposed to the external atmosphere, could trigger unforeseen chemical reactions or contaminate your own immediate environment if currents bring it back. You would have to store, process and compact all waste indefinitely, or find a way to launch it out of the atmosphere entirely, which brings us back to the impossible energy costs of escape. The hostile chemistry also means there is no possibility of using in situ resources for fuel. On Mars, you can make methane and oxygen from the atmosphere and water ice. On a gas giant, your propellant options are limited. You have plenty of hydrogen, but without oxygen, it's useless in a conventional rocket engine. You would have to bring your own oxidizer, again, from elsewhere. Nuclear thermal rockets using hydrogen are a possibility, but they require bringing fissionable material and present massive radiation hazards of their own. The planet offers no chemical help for leaving its grasp. In essence, the atmosphere of a gas giant is not an environment, it is an active chemical adversary. It offers nothing we need and presents everything we fear. It corrodes, it poisons, it explodes, and it suffocates. Our entire biological and technological framework is based on an oxygen-nitrogen chemistry, interacting with liquid water and solid minerals. The gas giant operates on a hydrogen-helium chemistry, with exotic phases of matter and violent electrical and thermal dynamics. The two are fundamentally incompatible. Colonization is not about adapting to a new environment, it is about bringing a tiny piece of our own environment and defending it with perpetual desperate effort against a world that is chemically designed to destroy it. The energy, the material strength, the logistical support required to maintain that bubble against the relentless chemical hostility is beyond any rational allocation of resources. It makes a lunar base or a Martian outpost look trivial by comparison. The chemistry alone, separate from the pressure, heat, wind and radiation, is a sufficient reason to declare gas giants off-limits for human settlement. They are wonders of the universe, demonstrating the incredible diversity of planetary formation, but they are also cosmic demonstrations of conditions that are the absolute antithesis of a habitable world. We can study their chemistry with spectrometers and probes, learning about the early solar system, but we can never, and should never, try to breathe it. All of these nightmarish conditions lead to a profound logistical reality that seals the deal, the challenge of simply getting there, and more importantly, ever leaving again. This isn't just a difficult journey, it's a one-way trip into a gravitational and atmospheric trap of the highest order. The process of entering a gas giant's atmosphere is an exercise in surviving a controlled demolition. Think about it. You're guiding a spacecraft from the cold vacuum of space into a deep gravity well, aiming for a point in a thick, swirling atmosphere. As you hit the upper fringes of that atmosphere, you're moving at incredible speeds, tens of thousands of miles per hour. All that kinetic energy has to go somewhere, and it is converted into heat through friction. This isn't re-entering Earth's atmosphere, which is challenging enough. This is hitting a wall of gas that gets thicker far more quickly. The heating is beyond extreme. The Galileo probe's heat shield experienced temperatures around 15,000 degrees Celsius during its entry, hotter than the surface of the Sun. That was for a small, sturdy, unmanned probe designed for a suicide mission. Now, scale that up to a ship large enough to carry colonists or construction materials. The heat shield for such a vessel would be monstrously large and heavy, and it would have to be absolutely flawless. Any crack, any uneven ablation, and the ship would burn up in a flash. The entry itself is a violent, unpredictable ordeal, with turbulence and G-forces that would test both human endurance and structural integrity to their absolute limits. But let's say you somehow nail the entry. You've dissipated that horrific heat, your main vessel or landing craft is intact, and you are now descending into the deeper atmosphere. Congratulations, you have just committed the ultimate act of cosmic parking. You are now in the gravity well. Getting out is a problem of a completely different and arguably greater magnitude. The gravity well of a planet like Jupiter is not a gentle slope, it is a sheer, deep pit. Remember, to achieve orbit from Earth, you need to reach a velocity of about 5 miles per second. To achieve orbit from just the cloud tops of Jupiter, you need a velocity exceeding 30 miles per second. That is 6 times the delta V, the change in velocity. The rocket equation is not kind here, it is exponential. For every pound of payload you wish to lift from Jupiter's atmosphere, you need an enormous amount of fuel. But that fuel itself has mass, which requires more fuel to lift it. The numbers quickly become absurd. A ship capable of launching from Jupiter's cloud tops back into orbit would be almost entirely fuel tank, with a tiny, tiny payload capsule. And this is from the cloud tops, the very top of the atmosphere. A colony, however, would not be at the cloud tops. To find a layer of sufficient density for buoyancy, you would need to descend dozens, perhaps hundreds of kilometers deeper. This is the critical trap. Launching from that depth is even harder. You're starting from deeper in the well. First, your ship would have to climb vertically through thousands of kilometers of dense, turbulent atmosphere, fighting drag and gravity all the way, just to reach the cloud-top starting point that already requires a 30 mile per second boost. This climb alone would require a staggering amount of energy, likely using some form of nuclear thermal or even more exotic propulsion just to push against the atmospheric drag. Then, once you reach the nominal surface altitude, you still have to perform the orbital insertion burn. The combined propellant needs are so astronomical that they render the concept of a return vehicle or even regular resupply shuttle flights a complete fantasy. The colony would be isolated from its inception. The ships that brought the first pioneers and their gear would be cannibalized for parts because they could never carry enough fuel to leave. This transforms the endeavor from colonization to exile, or a life sentence. The psychological impact of knowing there is no ticket home, no evacuation, no resupply that isn't a Herculean, once-in-a-generation effort would be devastating. It removes the safety net that enables exploration. On Mars, as harsh as it is, there is at least a theoretical possibility of a return journey with foreseeable technology. On a gas giant, that door slams shut behind you permanently. This also makes the construction of the colony itself a paradox. To build a large permanent structure, you need to deliver massive amounts of material, but delivering anything large is a problem of entry, and once it's down there forever. You couldn't send modular components and assemble them in orbit around Jupiter, and then lower them, because lowering them requires dealing with the entry heat all over again. You might try to manufacture materials in situ, but as we've discussed, the raw resources aren't there, so every beam, every panel, every bolt must be shipped in. The cost per kilogram delivered to the surface of Mars is high, but calculable. The cost per kilogram delivered to a stable depth in Jupiter's atmosphere is essentially infinite, because the technology to do it reliably and repeatedly doesn't exist and may never exist. The energy economics are bankrupt from the start. Furthermore, consider the risk profile. On Mars, a launch failure might mean a supply crate is lost. During a Jupiter entry, a failure means the complete destruction of a vessel that represents an enormous investment of resources and possibly human lives, with no chance of recovery. The margin for error is zero. This makes the initial setup and any subsequent expansion an exercise in gambling with the stakes being total ruin. The gravity well also affects communications. While not directly related to entry and exit, the depth and energy required to send a signal out of the atmosphere and across the solar system is increased, adding another layer of isolation. But the core of the issue is the trap. The planet's gravity and atmosphere form the most effective prison imaginable. It allows entry with brutal difficulty, but it effectively prohibits exit. Any colonization effort requires a two-way street, a connection to the wider civilization that supports it. A Martian colony could in theory be resupplied annually. The Jovian colony would be on its own after the first mission, for decades or centuries, until some inconceivable advancement in propulsion. This level of isolation is unsustainable for a technological colony that relies on external tools and materials. It would force a regression to a purely survival-based existence. But the environment is so hostile that survival itself requires high technology. It's a catch-22. You need advanced tech to live, but you cannot maintain or replace that tech without a supply chain, and the supply chain is impossible. So the colony would slowly degrade, its machines failing one by one, with no way to fabricate new ones until the final system fails and the environment claims everyone. This isn't a future. It's a very slow, very expensive method of group suicide. The challenge of entry and exit isn't just another item on a list of problems. It is the overarching logistical verdict on the entire idea. It declares that even if you could solve all the physical and chemical horrors, the act of getting people and materials there and maintaining a link to home is so prohibitively difficult that it collapses the rationale for going in the first place. Why would you send people to a place where you cannot retrieve them, cannot help them if something goes wrong, and cannot benefit from any resources they might theoretically find? The only scientific or economic activities that make sense are robotic, because robots don't need a return ticket and don't mind being destroyed at the end of their mission. The entry and exit problem frames the gas giant not as a new frontier, but as a roach motel for spacecraft. You can check in, but you can't check out. This transforms the romantic vision of floating cities into a grim tale of marooned pioneers waiting for inevitable systems failure. Our instinct is to explore, but a key part of healthy exploration is the ability to return, to report, to bring back knowledge and experience. A gas giant colonization mission sacrifices that return on a fundamental physical level. It is the ultimate dead-end mission. Therefore, when we add this to the list of other impossibilities, the conclusion becomes inescapable. The planets themselves, through their simple, immutable physics, have built the perfect defences against visitors who wish to stay. They are fortresses whose moats are gravity wells, and whose walls are storms of fire and poison. We can send our messages in bottles, our robotic probes, to crash against those walls and send back a few seconds of data before they are obliterated. But we cannot and should not send ourselves. The door is one way, and it leads only to a prison cell at the bottom of a deep, dark, violent sea. So while the dream of touching the clouds of Jupiter is a powerful one, the reality of the journey there and back makes it clear that this dream belongs to the realm of imagination, not engineering. Our destiny lies on solid ground, where the sky is above us and the stars are a destination, not a barred window from a cell we can never escape. That profound isolation we just described is compounded by a cruel irony. The very planets that are the largest in our solar system, colossal in their mass and volume, are paradoxically the most impoverished in terms of the resources we actually need to survive and build. This is the core of the resource paradox, an abundance of the wrong things and a dire scarcity of the right ones. A gas giant is a masterpiece of cosmic simplicity, composed almost entirely of the two lightest elements, hydrogen and helium. Together, these make up something like 99% of Jupiter's mass. For a star, this is the fuel for fusion. For a civilization that evolved on a rocky world, it is mostly useless. We are creatures of the rare elements, the ones forged in stellar furnaces and scattered by supernovae. Our technology, our bodies, our very concept of a tool is based on elements like iron, silicon, oxygen, carbon, nitrogen, and calcium. These are the elements of rock and metal, of water and air. On a gas giant, they are trace contaminants, lost in an overwhelming sea of hydrogen. Imagine needing to build a city. You need steel for structure, glass for windows, copper for wiring, silicon for electronics, concrete for foundations. On Mars, you can find the raw ingredients for many of these in the regolith. On an asteroid, you can mine metals. On a gas giant, you have none of that. There is no regolith, no bedrock, no accessible ore bodies. The heavier elements, the ones we call metals and minerals, have mostly sunk to the core due to the immense gravity over billions of years. That core, a ball of rock and metal perhaps 10 to 20 times the mass of Earth, is a fascinating scientific target. But it is also completely inaccessible. It is buried under tens of thousands of kilometres of progressively denser fluid, under pressures that crush matter into exotic forms, and temperatures that vaporise any known material. To reach it with any kind of mining operation is a fantasy beyond any engineering we can conceive. You cannot send a drill, you cannot send a robot, you cannot send anything that would not be destroyed long before it got close. So the very resources you need to build and repair your colony are locked away in the most impregnable vault imaginable, the planet's own heart. What does exist in the atmosphere? Besides hydrogen and helium, you have traces of methane, ammonia, water vapour, hydrogen sulfide and other simple compounds. These exist as gases, ices or droplets in the cloud layers. Could you use these? Possibly, but with extreme difficulty. You could crack methane for its carbon and hydrogen, or ammonia for its nitrogen, but the concentrations are low. To extract a single kilogram of carbon, you might need to process millions of kilograms of atmospheric gas. This requires enormous energy and massive processing facilities, which you would have to build from materials you don't have. It's a catch-22 of epic proportions. You need resources to build the machines, to extract resources, but you have no resources to build the machines. Everything must be imported, and the scale of importation is mind-boggling. A small self-sustaining colony of say 1,000 people would require thousands of tons of material just for the initial habitat structure, not to mention the machinery for life support, food production and energy. Every single gram of that material would have to be launched from Earth or another rocky world, hurled across the solar system, and then plunged through the atmospheric entry hell we already discussed. The cost in energy and money is unimaginable, dwarfing the GDP of entire nations for a single, fragile outpost. Compare this to a lunar base. The moon has regolith rich in oxygen, silicon, aluminum and iron. You can in theory build structures from lunar concrete, extract oxygen for breathing and rocket fuel, and use local materials for radiation shielding. Mars has water ice, carbon dioxide, and a regolith from which you could potentially extract various useful materials. These places offer a path to in situ resource utilisation, which is the only way colonisation becomes economically feasible. A gas giant offers no such path. It offers only consumption. Your colony would be a parasite, feeding off shipments from the outside until the political will or economic ability to send them collapses. Then the colony dies. There is also the critical resource of water. Water is the solvent of life, essential for drinking, agriculture and industrial processes. On a gas giant, liquid water as we know it does not exist in accessible reservoirs. Water molecules are present, but they are either frozen in high, cold cloud decks or dissociated into their components in the deep, hot interior. To collect useful amounts of water, you would again need to process vast volumes of atmosphere, a hugely energy-intensive task. You cannot simply dig a well. Even if you could find a layer where water droplets exist, collecting them in meaningful quantities from a hovering habitat in winds of hundreds of miles per hour is an engineering nightmare. So water too must be imported or painstakingly synthesized from atmospheric hydrogen and oxygen you've stripped from other compounds, which is again a circular problem of needing machines to make the machines to run the processes. The lack of solid land also means no possibility of agriculture in any traditional sense. You cannot have fields. All food production must be hydroponic or aeroponic, requiring every nutrient to be carefully imported and recycled. The nutrient cycles must be closed with near-perfect efficiency, a challenge we have yet to master, even in earthbound experiments like Biosphere 2. Any leak or loss of phosphorus, potassium or other vital nutrients would be irreplaceable from the local environment, leading to a gradual collapse of the food supply. The colony's biosphere would be a tiny fragile bubble entirely dependent on imported supplements. Energy is another resource that seems abundant but is terribly difficult to harness. Solar power is useless at that distance from the sun and beneath thick clouds. The internal heat of the planet is immense, but tapping into it is a different story. You would need to somehow use the temperature gradient between the hot depths and the cold upper layers, but as we've discussed, existing in that gradient is the problem. You could use nuclear fission, but that requires importing enriched uranium or plutonium. Fusion, if we ever master it, would require deuterium, which could be extracted from the hydrogen in the atmosphere. But the supporting technology for a fusion reactor is unimaginably complex, and would itself be built from rare elements you don't have locally. So even the seemingly simple act of keeping the lights on becomes a crisis of logistics. This fundamental lack of conventional resources redefines the gas giant from a potential home to a scientific curiosity. It is a place you visit with sensors, not with bulldozers and factories. Its value is in data, not in materials. The resources it holds, in abundance, hydrogen and helium, are only valuable if you have a use for them in space. Hydrogen could be used as rocket fuel, but you would need to pair it with an oxidizer, which you must bring. Helium-3, often cited as a potential fusion fuel, is present in the solar wind and might be trapped in the atmospheres of gas giants, but its extraction would again require processing colossal amounts of gas for trace amounts, and the fusion technology to use it remains speculative. The economic case vanishes when you consider the energy cost of extraction versus the energy gained. In the end, the resource landscape of a gas giant is a desert disguised as an ocean. It is vast, deep, and full of motion, but it yields none of the sustenance a human civilization requires. We are creatures of the crust, of the interface between rock, water, and air. The gas giants are homogeneous spheres where that interface never formed. To colonize them is not to adapt to a new environment, it is to attempt to recreate Earth in its entirety, piece by imported piece, inside a pressure cooker that is actively trying to destroy it. The scarcity isn't just an obstacle, it is the final, logical proof that these worlds were never meant for us. Our future lies in the rubble of the solar system, the asteroids, moons, and rocky planets where the universe deposited the building blocks we are made of. The gas giants will remain as they are, majestic, dynamic, and forever just out of reach, reminding us that in the cosmos, size does not equal utility, and that true abundance for a species like ours is found in the dirt beneath our feet, not in the endless, empty wealth of a hydrogen sky. So, faced with that absolute scarcity of solid resources, the most common idea to get around the lack of a surface is to float. It seems so elegant, so obvious. If you can't land, you hover. We imagine vast cloud-borne cities' delicate habitats suspended from balloons, or propelled by gentle fans, living in the skies of Jupiter like some science fiction dream. This is the concept of the floating habitat, using balloons, dirigibles, or some form of aerodynamic structure to maintain buoyancy at a specific layer of the atmosphere. It swaps the problem of a foundation for the problem of perpetual suspension. And while it sounds like a clever workaround, it's here, in the practical engineering, that the idea unravels completely. The first and most fundamental issue is finding the right layer to float in. Buoyancy works on a simple principle. An object will float if it is less dense than the fluid surrounding it. So, to float in a gas giant's atmosphere, your entire habitat, with all its people, machinery, shielding and structure, must have an average density lower than the atmosphere at that specific depth. This immediately creates a conflict. To be safe for humans, your habitat needs strong walls, thick radiation shielding, and lots of heavy equipment, all of which increase its density. To float, it needs to be light. You're constantly battling this trade-off. Now, where is this magical layer of just right density? It's not at the top. The upper atmosphere is too thin, like a wispy gas, so your habitat would have to be impossibly light, a piece of tissue paper that would be torn apart by radiation and micrometeoroids. To find sufficient atmospheric density to support a reasonably dense structure, you must descend, and as you descend, pressure and temperature rise. So the very act of going deep enough to float brings you into the domain of the crushing pressure and the hellish heat we've already detailed. There is no free lunch. The layer where the atmospheric density might match the density of, say, a submarine or a robust airship is already a region of extreme environmental hostility. You haven't avoided the problems, you've simply chosen to face them while trying to stay afloat. Then come the winds, the hypercanic winds we discussed. A balloon or dirigible on Earth can be tethered or can navigate slowly. In the jet streams of Jupiter, your floating habitat becomes a leaf in a perpetual hurricane. It has no anchor. It will be swept along at hundreds of miles per hour. This makes the concept of a colony with a fixed location meaningless. You're on a never-ending high-speed journey around the planet. If you have multiple habitats, they will be separated by thousands of miles in a matter of days, making travel and community impossible. To resist this, to try to maintain station or move against the wind, would require propulsion. But propelling a city-sized object against a several hundred mile-per-hour wind under crushing gravity and high atmospheric density requires engines of unimaginable thrust and energy consumption. You would need the equivalent of continuous rocket engines firing forever, just to stay in one spot relative to the planet's interior. The fuel for that does not exist, so you must go with the flow. But going with the flow introduces monstrous engineering challenges of its own. The habitat must be aerodynamic to reduce drag and turbulence, but it also needs to be spacious enough for people to live in for generations. These are contradictory design goals. A sleek, tear-shaped dirigible is not a good shape for interior living spaces, which tend to be boxes and cylinders for efficient use of volume. The external shape would be a compromise, likely inefficient at both tasks. The turbulence within these wind streams would subject the structure to constant, unpredictable buffeting and vibration. Every weld, every joint, every windowsill would be fatigued by this never-ending shaking. Maintenance would be a constant battle against metal fatigue and stress fractures. Now, consider the buoyancy system itself. Let's say you use a giant envelope filled with a lifting gas. On Earth, we use helium because it's inert and lighter than air. On Jupiter, the atmosphere is mostly hydrogen, which is already the lightest gas. So to get lift, you would need something even lighter than hydrogen, which means either hot hydrogen or helium. Hot hydrogen is a spectacularly bad idea in an oxygen-free but electrically active environment because of the fire risk, though the lack of oxygen mitigates that, but static electricity could still be an issue. Helium's better, but it's a non-renewable resource you'd have to import from elsewhere in the solar system. Your envelope must be absolutely perfect. A single puncture, whether from an abrasive ammonia ice crystal at 500 miles per hour, a micrometeoroid, or fatigue from pressure cycles would cause a leak. A leak means a loss of lift gas. As lift gas escapes, the habitat's average density increases and it begins to sink. This is not a slow leak on a hot air balloon where you can land. This is a sink into progressively higher pressure and temperature. You would have a limited time to repair the leak before you sink to a depth where the external pressure is too great for your structure, leading to implosion. Repairing a giant pressurized gas envelope in winds of hundreds of miles per hour is not feasible. You couldn't send people out there. Robotics might attempt it, but they would be operating in a violent, corrosive, high-pressure environment. It's likely a leak would be a death sentence for the entire colony. The envelope material itself is a huge problem. It needs to be incredibly strong to withstand the pressure differential, lightweight to not defeat the purpose of buoyancy, flexible to handle turbulence, and resistant to corrosion from ammonia and hydrogen sulfide. It must also be impermeable to helium, as helium atoms are small and can slowly seep through many materials. We have no material that meets all these criteria. Mylar or Vectron might work in theory for a short-term probe, but for a permanent habitat they would degrade under UV radiation, particle bombardment, and chemical attack. Then there's the issue of pressure control. As the habitat drifts, it might encounter atmospheric downdrafts or updrafts, which would change the ambient pressure outside rapidly. The internal pressure of your habitat is fixed for human comfort. The external pressure will fluctuate with weather and altitude changes. This means the pressure differential on your hull will change, sometimes dramatically. Your structure must be built to handle the maximum possible pressure differential it could ever encounter, which again means heavier, stronger materials. Alternatively, you could have a system to pump gas in or out of internal ballonets to adjust buoyancy and maintain a very constant depth, but that system adds complexity, weight, and another point of failure. The energy required to run these systems continuously is another drain on your already overstretched power grid. Let's talk about the psychological reality of such a life. You're not living in a city, you're living inside a machine that is one leak away from a death plunge. There is no solidity, no permanence. The world outside your window is a frenetic, streaking blur of clouds. You're in constant high-speed motion, but going nowhere, just circling the planet in a vast, endless storm. The sense of rootlessness and helplessness would be profound. There is no terra firma, only a perpetual, uneasy suspension over an infinite abyss. Even the day and night would be strange, filtered through thick, racing clouds with no familiar sunrise or sunset. The proposed floating habitat doesn't solve the problems of colonization, it merely exchanges one set of impossible problems for another. It trades the need for a foundation for the need for perpetual, flawless buoyancy in a violently unstable medium. It trades mining for mining the atmosphere, which is even less efficient. It trades stationary construction for a life adrift. It is, at best, a scenario for a temporary scientific outpost, a daring and likely suicidal mission for a handful of researchers to spend a few months collecting data before their inevitable demise. It is not a blueprint for a self-sustaining civilization. The floating habitat idea is a testament to human ingenuity and problem-solving, but it's also a demonstration of how some problems have no solutions, only increasingly elaborate ways to fail. The gas giant environment is so comprehensively hostile that every apparent workaround leads you back to another fundamental physical limit. You cannot cheat the need for resources, the need for stability, or the need for safety. The balloon habitat attempts to cheat all three, and in doing so becomes the most precarious and unsustainable form of habitation imaginable. Our future in space depends on building on firm ground, on worlds that offer at least some of the raw materials we need. The gas giants, for all their majestic beauty, offer only a lesson in humility, showing us that there are places where the very laws of physics conspire to make a home not just difficult, but utterly, unequivocally impossible. The floating city is a beautiful dream, but it will remain a dream forever confined to the realm of artists' impressions and science fiction novels, while our real efforts turn towards the silent, solid rocks of the inner solar system and the promising moons that orbit these very giants, worlds that, while challenging, at least have a surface to stand on. The floating habitat, for all its technical insanity, introduces a final, deeply human layer of impossibility, one that lives not in the metal of the hull but in the mind of the colonist. Let's assume a miracle, that we have solved the pressure with a magical material, managed the heat with infinite energy, shielded the radiation with massless armour, and stabilised a buoyant city against the eternal winds. The humans inside that technological bubble would then face an enemy no engineering can ever fully defeat, the psychology of eternal confinement in a hellscape. We're not built for this. Our minds evolved on the African savannah, under an open sky, with a horizon, with day and night cycles, with seasons, with the ability to walk in any direction and feel the sun and the wind on our skin. A gas giant colony provides the exact opposite of every single one of those needs. It is the ultimate sensory deprivation chamber mixed with the ultimate sensory overload of terror. First, there is the absence of a horizon, a stable visual reference. On a planet, even in desert or on the ocean, your eye finds a line where the sky meets the land or sea. It gives a sense of place, scale, and stability. In a floating habitat, your window, if you have one, looks out onto a perpetual churning murk. There is no horizon, only swirling bands of ammonia and ammonium hydrosulfide clouds rushing past at hundreds of miles per hour. The view is monotonous in its chaos, a dizzying, nauseating smear of browns, oranges and whites with no focal point. This alone can cause severe disorientation and vertigo over time. There is no outside to walk to. You're forever inside. You'll never feel natural sunlight on your face, only artificial light from lamps. You'll never feel a natural breeze, only the recycled, sterile air of the life support system. You'll never stand on soil, only on metal or composite deck plating. This profound sensory monotony, broken only by the frightening view of the external maelstrom, leads to a condition akin to what submariners or Antarctic winter overcrews experience, but magnified by orders of magnitude because there is no end date, no rotation home. This is forever. The knowledge that this metal can is your entire universe, and that beyond its thin skin lies instant death, creates a pervasive low-grade anxiety that can erode the strongest psyche. It is the ultimate form of cabin fever, with no cabin door to open. Every sound from the hull, every creak or groan from the structure, becomes a potential harbinger of doom. Is that just normal stress from the wind, or is it a support beam failing? The constant, unavoidable awareness of your fragility would be mentally exhausting. Furthermore, the environment outside offers no respite, no beauty, no solace. On Mars, a colonist could look out at the ruddy plains, the mountains, the sunset, and find a stark, alien beauty. It is a landscape. It has geography, has a sense of place. Looking out a port on Jupiter, you see no landscape, only weather. It is like living inside a tornado that never ends. The view is not inspiring, it is oppressive and menacing. The Great Red Spot isn't a wonder to admire, it is a monster larger than your world that could, in theory, swallow you. The external environment is not just hostile, it is aesthetically hostile, offering nothing to calm or uplift the human spirit. The lack of a day-night cycle as we know it further disrupts human biology and psychology. The planet rotates quickly, but the thick global cloud cover means there is no clear sunrise or sunset, just a gradual, gloomy brightening and dimming. Your colony would operate on an artificial 24-hour cycle, but your body's circadian rhythms are finely tuned to natural light cues. The disconnect can lead to sleep disorders, depression, and hormonal imbalances. There are no seasons, no changes, just the same endless, turbulent soup. This temporal flatness, the feeling of being stuck in a single terrifying moment for a lifetime, is psychologically crushing. Then there is the social and psychological impact of the knowledge of your situation. You're not a pioneer on a frontier you can tame. You're a prisoner in a maximum security facility of your own making. Every child born in the colony would be born into that prison, with no concept of a natural world, of open spaces, of walking without a suit, of feeling rain. They would be told stories of Earth, of forests and oceans, and it would sound like mythology. This could create profound generational alienation and a kind of cultural claustrophobia. The colony's entire purpose would be mere survival, with no possibility of expansion, no new frontiers to push against on the planet itself. There is no west to expand into, only more of the same lethal gas in all directions. This lack of a growth narrative, of a purpose beyond mere existence, is deadly to long-term societal cohesion. Human societies thrive on challenge and progress, but here the only challenge is not dying and progress is impossible. The stress would also manifest in interpersonal relationships. In an environment where a single argument could lead to a person sabotaging a critical life support system, trust is paramount and fragile. The pressure to conform, to never make a mistake, to never have a bad day would be immense. There is no walking it off outside. Every conflict is internalized with no release valve. The colony would need to be a utopia of human cooperation to survive. But we are not utopian creatures. We are messy, emotional, and sometimes irrational. The normal friction of human life becomes a critical systems risk in such a closed environment. The psychology of risk itself changes. On Earth, we take small risks every day, crossing a street, driving a car. In the colony, there are no small risks. Every action is mediated by safety protocols. The freedom to make a mistake, a fundamental part of learning and living, is gone. This creates a society of extreme caution and anxiety, stifling innovation and creating a culture of fear. Ultimately, the human mind needs a connection to something larger than itself, a sense of place in the cosmos. On Earth, we have the sky, the stars, the sun, the moon. In the depths of a gas giant, you have none of that. You are buried in an atmosphere. You cannot see the stars, ever. You cannot see other planets. Your universe is the interior of your habitat and the storm outside. This is a profound existential isolation. You're not on a world looking up at the universe. You're in a pit, looking at the walls of the pit. This can lead to feelings of insignificance and despair that are far more acute than those experienced in space, where you can see the infinity of the cosmos. In space, you feel small but connected. In the gas giant, you feel small and buried. The proposed solutions, like virtual reality windows showing Earth scenes, are band-aids. They're constant reminders of what you have lost forever, not a substitute for reality. They might help for a while, but the cognitive dissonance between the peaceful VR meadow and the shuddering, roaring reality of your actual surroundings would be psychologically jarring. In the end, the psychological environment is as uninhabitable as the physical one. We could perhaps design a machine to survive the pressure, heat, and radiation, but we cannot redesign the human mind to thrive in perpetual helpless confinement inside that machine, adrift in a perpetual storm. The colonists wouldn't be pioneers. They would be inmates in the most secure prison ever conceived, one where the walls are made of hurricane and the guards are the laws of physics. No society could remain healthy or sane under such conditions for multiple generations. The mental breakdown, the social collapse, would be a certainty long before any physical system failed. Therefore, even if the physics could be conquered, the psychology cannot. This is the final human verdict on gas giant colonization. We are not just bodies that need oxygen and pressure. We are minds that need sky and earth, horizon and hope, and a world that does not constantly whisper of our imminent obliteration. The gas giant offers none of that, only a cage of endless fury. Our destiny lies under open sky, even if that sky is on Mars or under the dome of a lunar crater, places where the human spirit, not just the human body, has a fighting chance to feel at home. That psychological strain is inextricably linked to the most fundamental physical need, the need to eat and breathe. This isn't just about stocking enough food for a long mission. It's about creating an entire self-sustaining biosphere from scratch, in a place where nature provides absolutely nothing to build upon. On Earth, our biosphere is a vast, interconnected and forgiving system. Plants grow in soil using sunlight, carbon dioxide and minerals from the ground. Animals eat the plants, and their waste returns nutrients to the soil. The atmosphere is replenished by plant life, and water is cycled through evaporation and rain. In a gas giant colony, you have none of that foundation. You have to create a tiny, closed, and perfectly balanced replica of Earth's complexity inside a sealed can, and then keep it running forever without a single critical failure. This is perhaps the most daunting technical challenge of all, dwarfing even the pressure hull because it involves managing the chaotic living systems upon which every colonist depends every second. First, consider agriculture. There is no soil. There is no dirt. Every gram of growing medium must be imported. This likely means hydroponics or aeroponics, where plant roots are misted with or suspended in a nutrient-rich water solution. This is efficient in terms of water and space, but it is utterly dependent on that nutrient solution. Every essential element for plant growth, nitrogen, phosphorus, potassium, calcium, magnesium, and a suite of micronutrients like iron and zinc must be included. On Earth, these nutrients are continuously recycled and replenished from the weathering of rocks and the decomposition of organic matter. In your closed colony, there is no external source. Every atom must be recovered and reused. When a colonist eats a plant, they excrete waste. That waste must be processed with near total efficiency to recover every single nutrient molecule and return it to the hydroponic tanks. Any loss, Any inefficiency in the recycling loop means a slow, inexorable drain of vital elements. Over time, your nutrient solution becomes depleted and your crops fail. You cannot go outside and mine for more phosphorus. You either brought a finite supply with you, which will run out, or you have a magical 100% perfect recycling system, which has never been achieved. The failure of even one component in the waste processing system, a clogged filter, a bacterial die-off in a bioreactor, could interrupt the cycle and doom the food supply within weeks. Then there's the issue of energy for growth. Plants need light for photosynthesis. There is no meaningful sunlight at that depth in a gas giant. It's perpetually dark, so all light must be artificial. Growing enough food to sustain a population requires enormous amounts of electric light. The energy requirements are staggering. For a colony of 1,000 people, you might need the equivalent of dozens of football fields of densely lit grow racks. All that electricity must come from somewhere, likely nuclear reactors, which themselves produce waste heat that you must dump into an already hot environment. The lighting systems generate heat too, adding to your thermal management nightmare. The entire agricultural sector becomes a massive, energy-intensive machine that is the colony's lifeline and its single largest power drain. The air they breathe is another closed loop. Humans consume oxygen and exhale carbon dioxide. Plants do the reverse, but the scales have to match perfectly. Your agricultural volume must be large enough to reprocess all the carbon dioxide from the colonists and produce enough oxygen for them to breathe. But plants also respire, consuming oxygen at night. The system is dynamic and requires careful monitoring and buffering. Any imbalance, a crop failure that reduces plant mass, or a fire that consumes oxygen rapidly, could fatally alter the atmospheric composition. You would need large, pressurized buffer tanks of oxygen and carbon dioxide to smooth out these fluctuations, but again, these are finite reserves. The system must be in perpetual, precise balance. Water is the bloodstream of this closed ecology. It is used for drinking, for hydroponics, for humidity control, and for industrial processes. It must be recycled with incredible efficiency. On the International Space Station, water recovery is around 90 to 95%. That's good for a temporary outpost being resupplied from Earth. For a permanent, isolated colony, you might need 99.9% recovery. Every drop of sweat, every bit of moisture and exhaled breath, every bit of urine must be captured, purified, and reused. Any leak or loss is a permanent subtraction from your total life-supporting water mass. And remember, you can't just condense water from the atmosphere outside, because the outside atmosphere is a toxic mix containing very little water vapour, and what's there is contaminated with ammonia and other chemicals. The history of attempts to create closed biospheres is sobering. The most famous, Biosphere 2 in Arizona, was a massive, sealed structure built to test whether a complex ecosystem could sustain 8 humans for 2 years. It failed spectacularly in several ways. Oxygen levels dropped dangerously because soil bacteria consumed it faster than the plants could produce it, requiring oxygen to be pumped in from the outside. Nitrous oxide levels rose to brain-impairing levels. Many plant and animal species went extinct. Pests like cockroaches and ants thrived. The biospherians faced hunger and interpersonal conflict. And this was on Earth, with a full spectrum of sunlight, in a controlled environment built by the best scientists and engineers of the time. It was a humbling lesson in how poorly we understand the intricacies of even our own biosphere, let alone how to recreate a stable miniature version. Now, imagine attempting that same experiment, but instead of a large sunlit structure in the Arizona desert, it's inside a pressurized can suspended into the dark, supercritical atmosphere of Jupiter, with orders of magnitude less margin for error. The introduction of any contaminant from the outside environment would be catastrophic. A tiny leak that allowed even a small amount of ammonia or hydrogen sulfide into the habitat's atmosphere could poison the plants, corrode equipment, and sicken the colonists. There is no outside to vent to cleanse the system. A mold or bacterial pathogen that attacks your primary food crop could wipe it out before you can respond, and you have no backup fields, no alternative ecosystems to draw from. Your seed bank is your only genetic repository, and if a pathogen gets into that, you're finished. The social and psychological pressures we discussed earlier directly impact this biological system. A depressed colonist neglecting their duties in the hydroponics bay could cause a crop failure. Sabotage, however unlikely, becomes a species-ending threat. The stress of maintaining this perfect balance would be immense, turning every gardener into a life support technician and every meal into a testament to a system perpetually on the edge of collapse. In contrast, consider a Mars colony. It has a surface. It has regolith that can be processed into soil. It has water ice. It has carbon dioxide in the atmosphere that can be processed into oxygen and carbon for plants. It has sunlight, dim but usable, that can be supplemented with artificial light. It offers a path to true in situ resource utilisation for a biosphere. A gas giant offers nothing but a void. Your entire biosphere is an import, a delicate, manufactured bubble of Earth life, trying to exist in a space that is the absolute antithesis of a habitat. It is the ultimate expression of human arrogance, to believe we can not only survive in such a place, but recreate the entire complex web of life that supports us in miniature without error forever. The impossibility of agriculture and a closed biosphere is the final practical nail in the coffin. It demonstrates that even if you could solve the structural and environmental problems, you cannot solve the problem of life itself in such a place. We are not just building a shelter, we are trying to bottle an ecosystem, and the gas giant is the last place in the solar system where that bottle could ever be stable. Our future lies on worlds where we can work with nature, however harsh, to build a life, not in places where we must invent nature itself from whole cloth while fighting a world that wants to erase it. Building and maintaining that impossible closed biosphere leads us to the ultimate, practical question, the one that exists outside the realm of pure physics and engineering, the question of cost and ethics. Why would we even try? Given the staggering, perhaps infinite difficulty of every single aspect we've outlined, what possible rationale could justify pouring the collective resources of humanity into such a quixotic, almost certainly fatal endeavour? This is where the dream crashes against the hard rocks of economics, ethics and simple logic. The resources required for a gas giant colonisation attempt, even a modest one, would be beyond colossal. We are not talking about the budget of a single nation space program. We are talking about the sustained economic output of a global civilization for generations. Think of the Apollo program, which at its peak consumed around 4% of the United States federal budget. Now imagine a project that makes Apollo look like a school science fair. The development of materials that don't exist, the construction of spacecraft larger than anything ever built just to deliver a tiny payload through atmospheric entry, the creation of a completely self-contained biosphere and power system, the logistics of a supply chain stretching over 500 million miles, all of it would require trillions upon trillions of dollars, euros, or whatever currency you use. It would demand the focus of our best scientists and engineers for a century, redirecting talent and innovation from every other field of human need. Medicine, energy, computing, environmental restoration, you name it. The opportunity cost is astronomical. Every dollar and every brain cell spent trying to solve the unsolvable problems of living on Jupiter is a dollar, and a brain cell not spent solving the very real problems we have here on Earth, or on building achievable, sustainable footholds on more hospitable worlds. It is the very definition of a misallocation of effort. Then there is the profound ethical dimension of risk. We are talking about sending human beings, with families and dreams, into an environment where the failure of any one of a million systems means a gruesome and immediate death for everyone. There is no rescue mission. There is no abort and return. It is a one-way ticket into a known extreme hazard. The ethical framework for human exploration involves informed consent and an acceptable level of risk, but this far exceeds any acceptable level. It would be sending people into a known, guaranteed death trap, where the probability of a catastrophic failure over a multi-year mission approaches 100%. Could anyone truly give informed consent for that? Could you look a volunteer in the eye and say, "You will live in constant terror. You will never see the sun or the stars again. Your children will be born in a metal prison, and it's almost certain you will die horribly when, not if, something goes wrong." This moves beyond exploration into the realm of recklessness with human life that most societies would find morally repugnant. It would be a spectacle of human sacrifice dressed up as progress. Furthermore, the ethical calculus extends to the resources themselves. In a world still struggling with poverty, inequality and climate change, what is the moral justification for spending a significant fraction of humanity's wealth on a vanity project with zero tangible return? The argument for space exploration often hinges on spin-off technologies and inspiring new generations. But those benefits can be achieved far more efficiently and safely by focusing on targets that are actually within reach, like the Moon or Mars. The spin-offs from trying to build a pressure hull for Jupiter would likely be negligible because the solutions would be so hyper-specialised to an environment that exists nowhere else. You wouldn't get a better refrigerator or a new medical device. You'd get a formula for a metal alloy that only works at pressures and temperatures that are irrelevant anywhere but in the heart of a gas giant. The inspiration would quickly turn to horror as the public watched a live feed of a doomed colony's final moments. There is also the ethical consideration of what we are trying to prove. Is the goal to demonstrate that we can live anywhere, no matter how hostile? That is a form of technological hubris that ignores the wisdom of choosing the right battles. True intelligence isn't about overcoming every obstacle through sheer force. It's about recognising which obstacles are meant to be bypassed. The gas giants are not a challenge to be met, they're a signpost saying go around. Our efforts should be focused on places where we can actually build a future, not just a tomb. Compare the cost and ethics to the alternatives. For a fraction of the cost of a Jovian cloud city, we could establish a permanent, growing presence on Mars. We could build rotating space habitats in the asteroid belt, with simulated gravity and abundant solar power, using mined asteroid resources for construction. We could establish research bases on the moons of the gas giants themselves, like Europa or Titan, worlds with solid surfaces and fascinating resources. These are hard, expensive problems, but they're problems with solutions grounded in known physics and incremental engineering. A Mars colony faces radiation, low gravity and dust storms, but it has a surface, raw materials and sunlight. An O'Neill cylinder space habitat requires massive construction, but it can be built in the benign environment of microgravity, tailored to human needs from the start. These paths offer a realistic vision of a multiplanetary future where humanity expands and thrives. A gas giant colony offers only a vision of perpetual desperate struggle ending in inevitable failure. The ethical choice is clear: direct our ambition, our courage, and our resources toward futures that have a chance of success and sustainability. Investing in gas giant colonization isn't just difficult, it's actively harmful to the broader project of space exploration. It would suck the oxygen out of other viable programs. It would become a budgetary black hole, a mega project that consumes everything and delivers nothing but tragedy. It could set back public and political support for space exploration for generations when, not if it fails. Why would we risk that? The pragmatic path forward is to continue what we're already doing so well, robotic exploration. Probes like Juno and Cassini have returned more knowledge about the outer solar system than 100 human-sent or Titan missions could have at a fraction of the cost and with zero risk to human life. We can design probes to dive deeper, to take more samples, to orbit for longer. We can explore the fascinating moons with landers and rovers. This is how we satisfy our curiosity and gain scientific understanding of these distant worlds. The data we get from robots is pure, unbiased by the need to keep humans alive. It is a better return on investment in every single way. In the end, the question of cost and ethics brings us back to a fundamental truth about our place in the universe. We are a species born of a very specific, narrow set of conditions. Our greatness lies in our adaptability, but that adaptability has limits. It is not a failure to recognize those limits. It is a sign of maturity. We do not need to conquer every environment to prove our worth. Our worth is proven by our wisdom to choose habitats that can sustain not just our bodies, but our societies, our cultures, and our spirit. The gas giants, for all their majestic scale, do not make that list. They are wonders to be studied, not deserts to be made bloom. The cost is too high, the risk is too great, and the ethical burden is too heavy. Our future is on the solid grounds of moons and planets, and in the constructed heavens of space stations, forever looking out at the swirling giants in the distance, appreciating their beauty from the safety of a home that was meant for us. This logical and ethical imperative to focus our efforts wisely leads us directly to the most compelling and realistic alternative, the moons. The gas giants themselves may be forever out of reach, but they are not solitary monarchs. They are kings with vast, diverse courts. Jupiter and Saturn are each orbited by dozens of moons, and some of these worlds are not mere rocks. They are complex, fascinating places that offer challenges we can actually overcome. This is the crucial strategic shift. from the impossible dream of colonizing the planet to the viable project of colonizing its system. The moons transform the gas giants from dead-end destinations into centres of gravitational influence, around which a truly sustainable human presence in the outer solar system could one day be built. Think of it not as failing to conquer Jupiter, but as recognising that the real estate of value orbits it. Take Europa, for example. It is a world covered in a global shell of water ice, cracked and streaked with reddish material. Beneath that ice, scientists are almost certain lies a vast salty ocean, possibly holding twice as much liquid water as all of Earth's oceans combined. This ocean is kept liquid by tidal heating, the gravitational kneading from Jupiter and its sibling moons. The challenges of Europa are immense. The surface is bathed in intense radiation from Jupiter's magnetosphere, and the ice shell could be many kilometres thick. But these are challenges with conceivable solutions. You could land a habitat on the surface, drill or melt through the ice, and establish a subsurface base in the ocean itself, shielded from radiation by the ice above. The water provides radiation shielding, a potential source of oxygen through electrolysis, and a medium for possibly fascinating if simple alien life. The point is, there is a surface to land on, and a resource, water, in almost unimaginable abundance. Then there is Titan, Saturn's largest moon. Titan is a world with a dense atmosphere, thicker than Earth's, composed mostly of nitrogen with a little methane. It has rivers, lakes and seas of liquid methane and ethane on its surface. It has a solid water ice bedrock and dunes of organic hydrocarbons. The atmosphere provides natural shielding from radiation and space debris. The presence of abundant carbon, hydrogen and nitrogen means you have the basic building blocks for plastics, fuels, and possibly even a form of agriculture using hydroponics with local water ice. The gravity is low, about 1/7 of Earth's, which makes construction and launch easier. Yes, it is cryogenically cold, minus 180 degrees Celsius, and the chemistry is exotic, but these are engineering problems, not fundamental physics-breaking paradoxes. You can design heaters and insulation. You can design suits and vehicles for a cold hydrocarbon environment. You have a landscape to explore, to build upon, to map. The colony on Titan could be a centre for studying prebiotic chemistry and for launching further exploration into the Saturnian system. These moons offer what the gas giants never can, a foundation. They have solid ground that changes everything. With solid ground you can anchor structures. You can lay out habitats in a stable configuration. You can mine local materials, water ice for life support and radiation shielding, silicates and metals from differentiated cores for construction. You can build large, permanent facilities without worrying about perpetual buoyancy or being swept away by eternal hurricanes. The presence of local resources is the key to sustainability. On Titan, you could potentially use the atmospheric methane as a fuel, cracking it for hydrogen or burning it with oxygen derived from water ice. On Europa, the water itself is the primary resource. On other moons, like Callisto, you have relatively radiation-quiet surfaces from which to operate. These are places where in-situ resource utilization moves from a fantasy to a planned reality. The psychological environment, while still alien and challenging, would be fundamentally different. On Titan, a colonist could put on a warm suit and walk outside onto a real landscape. They could see a horizon, even if the sky is orange and hazy. They could watch the slow movement of Saturn in the sky. They would have a sense of place, of being on a world, not in a machine adrift in a maelstrom. This connection to a physical, explorable environment is critical for long-term mental health and a sense of purpose. Furthermore, these moons provide the perfect vantage points for studying the gas giants themselves. A research base on Callisto or Titan is a safe, stable platform from which to operate fleets of robotic probes, atmospheric drones, and orbital observatories focused on Jupiter or Saturn. You get all the scientific benefits of proximity without any of the suicidal drawbacks of trying to inhabit the planet. The colony supports the science, and the science can support the colony economically and intellectually. This approach also aligns perfectly with a logical stepping stone strategy for human expansion. We learn to live and work on the moon, dealing with radiation and low gravity in a nearby manageable environment. We then tackle Mars, learning planetary-scale settlement on a surface with resources but a thin atmosphere. After mastering those environments, the next leap could be to the asteroid belt or the moons of the gas giants. Each step builds on the previous one, using technologies and lessons learned in a progressive and sustainable way. Jumping directly to a gas giant atmosphere skips all those necessary learning steps and attempts the hardest possible challenge first, a recipe for certain failure. Economically and ethically, focusing on the moons makes infinitely more sense. The development costs, while still enormous, would be for technologies with wider applications, pressure hulls for subsurface ocean bases, cryogenic engineering for Titan, in situ resource extraction techniques for water and volatiles. These technologies would be useful on many other worlds. The risk to human life, while still significant, is within a realm of calculated mitigated risk, not guaranteed sacrifice. Colonists would have a realistic chance of building a home, not just maintaining a doomed outpost. In essence, the moons represent the future of humanity in the outer solar system. The gas giants represent only a spectacle. By colonizing the moons, we turn the entire Jovian or Saturnian system into a domain of human activity. We can have research stations, mining outposts, and even thriving colonies spread across multiple moons, connected by transport networks. The gas giant becomes the gravitational heart of a new frontier, its fierce energy and radiation a natural barrier that defines and contains our sphere of activity, not a barrier we must foolishly try to cross. This is the mature strategic vision. It accepts the limitations imposed by physics on our bodies and our machines, and it leverages the opportunities that physics does provide. It replaces the impossible dream of floating cities with the achievable dream of subsurface habitats on Europa, or methane port settlements on Titan. So, when we talk about the legacy of the gas giants for humanity, it is not a legacy of habitation, but one of enablement. Their gravity holds captive a collection of some of the most interesting real estate in the solar system. Our future there lies on those captive worlds, in their ice and rock, not in their masters' skies. By looking past the brilliant, distracting clouds of Jupiter and Saturn, we find our true destiny in the silent, solid, and resource-rich moons that circle them, waiting for the touch of a species wise enough to build where the universe has provided the foundations. This brings us to the final and most important point of all, the legacy we've already begun and must continue, the legacy of robotic exploration. This isn't a consolation prize, it is the winning strategy. While human colonization of the gas giants is a fantasy, their scientific exploration through robotics is one of the great success stories of our space age, and it is the only path that makes sense for the foreseeable future. The story of our understanding of Jupiter and Saturn is not written in the journals of cloud-bound colonists. It is written in the data streams from pioneers like Pioneer, Voyager, Galileo, Cassini, and Juno. These missions have transformed these distant points of light into complex dynamic worlds we can begin to comprehend, and they have done so without risking a single human life. This robotic approach is not a compromise, it is the optimal tool for the job. Let's look at the record. The twin Voyager probes, launched in the 1970s, provided the first breathtaking close-up views of Jupiter's swirling clouds, its intricate ring system, and the volcanic activity on its moon, Io. They discovered the complexity of Saturn's rings and the thick atmosphere of Titan. These were flybys, quick glimpses that revolutionized planetary science. Then came Galileo, which did something astonishing. It orbited Jupiter for 8 years, studying its atmosphere, its magnetosphere, and its moons in incredible detail. It released a probe that plunged into the Jovian atmosphere, sending back data about composition, temperature, and wind speed until it was crushed. That probe's sacrifice taught us more about the deep atmosphere in 1 hour than centuries of telescope observation from Earth. Then there was Cassini, a masterpiece of engineering that spent 13 years orbiting Saturn. It revealed the staggering complexity of Saturn's rings, discovered geysers erupting from the moon Enceladus, mapped the lakes of Titan, and conducted countless other experiments. Its mission ended with a deliberate plunge into Saturn's atmosphere, gathering unique data until the very end. And now, Juno, orbiting Jupiter in a unique polar orbit, peering beneath the cloud tops with its microwave radiometer, mapping the gravitational and magnetic fields to unravel the secrets of the planet's interior structure. Every single one of these missions was a triumph of remote exploration. They were expensive, yes, but they were a fraction of the cost of a single human mission to the same destination, and they carried no life support, no return vehicle, no safety margins for human survival. Every gram of their mass was dedicated to science. They could be sent on trajectories that would be lethal for humans. They could operate in radiation zones that would kill a crew in days, and they could be commanded to perform terminal destructive maneuvers that yielded priceless final data. This is the model for the future. Instead of dreaming of cities in the clouds, we should be planning and funding the next generation of robotic explorers. More sophisticated orbiters with even better instruments. Advanced atmospheric probes that can go deeper and survive longer, perhaps using new materials or innovative cooling systems. Penetrators that could lodge into the ice moons and analyse their composition. Sample return missions from the moons like Enceladus or Europa, bringing pieces of those worlds back to Earth for detailed study in our laboratories. These missions are where the real, tangible scientific return on investment lies. The argument for robotics is overwhelming on every level. Safety is the most obvious. Robots don't die. They don't get radiation sickness. They don't suffer from muscle atrophy. And they don't experience psychological trauma. This allows us to take risks and go places we would never, ever send a human. Cost is the second pillar. Developing the technology to keep humans alive in space is the single most expensive part of any crewed mission. You need redundant life support, radiation shielding, food, water, waste recycling, exercise equipment, and a safe return vehicle. A robotic mission strips all that away. The budget for a flagship robotic mission like Cassini might be a few $1 billion. The budget for a human mission to the same destination, with its colossal life support and safety infrastructure, would be hundreds of billions, if not trillions. For the price of one impossible human expedition to Jupiter's clouds, we could fund a fleet of 12 robotic missions, each exploring a different aspect of the Jovian system, yielding far more science for our money. Focus is the third advantage. A human mission is ultimately about keeping the humans alive. The science, while important, becomes a secondary objective. Most of the mission's energy, mass and planning are consumed by the logistics of life support. A robotic mission is 100% science. Every system, from its power source to its communication antenna, exists to serve the instruments. This purity of purpose leads to more efficient and effective exploration. Furthermore, robotics allows for patience and longevity. A human mission has a strict timeline dictated by consumables and crew health. A robotic mission like Cassini or Juno can operate for years, even decades, observing long-term changes in weather patterns, ring dynamics, and magnetic field variations. This longitudinal data is invaluable and impossible to gather on a short human expedition. The technological spin-offs from robotic exploration are also significant and often underappreciated. The need for miniaturized, radiation-hardened electronics, autonomous navigation software, advanced imaging systems, and precision guidance for planetary flybys has driven innovation in numerous fields. These technologies find applications in medicine, computing, and Earth observation. While the spin-offs from a hypothetical gas giant habitat would be bizarre and hyper-specialized, the spin-offs from advanced robotics are broadly useful. There is also a philosophical and ethical clarity to robotic exploration. It represents a mature relationship with the cosmos. It acknowledges that some places are for knowing, not for occupying. It satisfies our innate curiosity, our drive to explore and understand our surroundings, without the colonialist baggage of claiming and conquering every rock and cloud we see. We can be stewards and students of the solar system, not just occupants. This approach also preserves these alien worlds in their natural state. The moons of the gas giants, especially those with potential subsurface oceans like Europa and Enceladus, are pristine laboratories for astrobiology. Sending human colonies there risks forward contamination, introducing Earth microbes that could compromise future searches for indigenous life. Robotic explorers can be meticulously sterilized, minimizing this risk. Our quest should be to find life, not to accidentally replace it with our own. So, what does the future hold? Imagine a fleet of drones, small and resilient, flying in the upper atmospheres of Jupiter or Saturn, taking detailed measurements of wind patterns and chemistry over many years. Imagine landers on the surface of Europa, melting their way through the ice to release autonomous submersibles into the dark ocean below. Imagine sample return capsules being launched from the surface of Titan, carrying fragments of its organic-rich dunes back to waiting scientists in orbit around Earth. These are the visions we should be funding and pursuing. They are difficult, but they are possible. They extend our senses to the farthest reaches of the solar system without extending our fragile bodies into environments that would destroy them. The acceptance of this robotic future is not an admission of defeat, it is a celebration of human ingenuity. It is saying that our greatest tool is not our ability to endure, but our ability to build machines that can go where we cannot and report back. The gas giants will forever be out of reach for human settlement, but they're wide open for human understanding mediated through the electronic eyes and hands of our robotic ambassadors. This is the true legacy, a legacy of knowledge, not of footprints. It is a legacy built on the courage of engineers who launch their creations into the void, and the patience of scientists who piece together the story of another world from bits of data. So let us abandon the childish dream of conquering the giants and embrace the mature, thrilling and profoundly productive reality of knowing them through the machines we send in our stead. Our future in space is a partnership between human curiosity and robotic capability, and in that partnership we can unlock the secrets of the universe without paying an impossible price. The giants will continue their eternal dance, and we will watch, learn and marvel from a safe and sensible distance.